Good morning, sir. Oh, sorry. वीडियो नहीं हुआ मैं कर लेती हूँ ना। ओके मैडम।
Hello, good morning. Good morning to all of you. Start कर देंगे है ना? Okay. Good morning to all of you. On behalf of the Department of Physics, JN College, I would like to welcome Dr. Milorai Modi, the principal of our college, and the vice principal of our college, Dr. S.D. Chowdhury, and also Dr. D.P. Panda, the coordinator of IQAC cell, and all the faculties of physics department, today's speakers, and also Dr. Sanjeev Kumar, who is the head of the department of Rajiv Gandhi University, and all the dear participants who have gathered to watch this webinar program. I would like to welcome all of you, and I take this privilege to welcome each and every one of you for this 3 days webinar program, which has been organized by the Department of Physics. And this, as short brief welcome note I would like to give. In this program, we have 70% of students, which includes the UG and the PG students, and 10% are research scholars, and around 10% are faculties from physics department from all over the country, and 10% from other. And the target audience here are mainly the students from PG and UG. And this program is organized by Dr. Yana and Mr. Enoch Libang from our department. We have the privilege that these two coordinators have been working hard to organize this program. And we have very renowned speakers from NERIST, NIT, and Cotton University, Assam, Tinsukia College, Assam, University of Delhi, and we have two speakers and also one speaker from Hanyang University, South Korea. Okay. I hope this program, in this program, the speakers will enlighten us with their knowledge and with their valuable wisdom. And I request all the participants to make use of this valuable opportunity, because such programs are very rare to get, especially in the Northeast region. So kindly make use of this opportunity, and I request all the participants to refresh your knowledge and to know new things through the talks of this good speakers that we have arranged. So with this short note, I would like to welcome once again all of you. And now I will request, and I would like to call upon our Vice Principal, Sir, Dr. S.D. Chowdhury, to give his speech. Thank you.
Namaskar and good morning to all of you. It's my great pleasure and honor to inaugurate the 3 days webinars lecture series on advancement and innovations in modern physics. It's my great pleasure to be a part of this great occasion when many brilliant minds would talk on advancements and innovations in modern physics. Even though I'm not a student of physics, I teach history in this college, and I've been teaching history for the last 28 years. I had also the privilege of studying physics as a school student, but the intricacies of physics acquired my mind, and the difficulties understanding the physics is a bit too hard. But still then, I take this, this morning I came to know that there are around 375 participants, and out of which 70% of them are students of the undergraduate and the postgraduate studies. So, and I believe that all these students, in very large number, would be benefited by the exchange of ideas in advancement and innovations in modern physics. Physics as is a very broad subject and is used heavily in engineering, acoustic, cosmology, and even in the Nobel Prize of Physics in 2019 was awarded for the contribution to the people's understanding of the evolution of the universe and the Earth's place in the cosmos, and for the discovery of an exoplanet and biting a solar-type star. The understanding and the use of acoustics results in sound control and better concert halls. Now, I'm given to understand, and I Googled a bit about physics. I came across a gentleman belonging to the 6th century Europe, Mr. John Philoponus, a Byzantine scholar, who first time, if I'm correct, but if I'm wrong, please don't underestimate me, because I don't teach history. He questioned Aristotle's teaching of physics and noted its flaws. He introduced what I'm told, the theory of impetus. Aristotle's physics was not scrutinized until Philoponus appeared. And unlike Aristotle, who based his physics on verbal argument, Philoponus relied on observation. Now, today's webinar on advancement and innovations in modern physics, in which many renowned personalities, resource persons from distinguished and famous universities and institutions will participate, will share their thoughts in the various aspects of modern physics, will certainly give a new impetus to the study of physics in this particular state. And sorry, taking advantage of the severe pandemic situation that is going on in our country and across the whole world, I congratulate the Department of Physics, led by the head of the department, Dr. S. Jayanti, to have initiated this webinar lecture series on advancement and innovations in modern physics. And I wish this webinar a very grand success. Thank you, ladies and gentlemen. It's my great pleasure. Good morning.
Thank you, sir, for your valuable and encouraging words regarding this webinar program. Your presence here is a great encouragement for all of us, and even our principal always encourage us to conduct such programs, and the college has been so helpful and encouraging all the departments to organize such webinar programs. So we are really thankful to our principal and vice principal for your presence and for all your encouragement. Now I would like to give the time to our IQAC coordinator, Dr. D.P. Panda, for his short sharing regarding this program.
Very good morning to one and all. Our respected Principal Sir, Vice Principal Sir, entire Physics Department. So in the outset, I would like to congratulate the Department of Physics for their endeavor in organizing such an excellent webinar, Advancement and Innovations in the Modern Physics. So the department led by Dr. Jayanti, the coordinators of the program, Mr. Renu Klibang, Dr. Anna Bagbi, and other faculties. You have done a very excellent work by selecting the most pertinent topic, which definitely enhance the quality of the students, the quality of the faculties, the quality of the researchers, undoubtedly. At the time of pandemic, the teaching learning process should not be stopped. You have proved it. So from the very core of my heart, I congratulate all of you. So definitely, this modern advancements and innovations in physics, it will act as a brainstorming for the students, for the researchers to acquaint themselves the modern innovations worldwide. I think the eminent speakers from our country and abroad will definitely give certain cues which will help the students of physics as well as the researchers. So I wish all the success of this 3 days webinar. Thanks to all.
Thank you very much, Dr. D.P. Panda, sir, for your valuable words of encouragement to our department. IQAC Cell has been really a source of blessing for all the departments, especially for the Department of Physics, because IQAC has been supporting us in sponsoring a huge amount of money for organizing such programs and encouraging every department, especially the Department of Physics, for organizing many programs. That has been really helping the faculties and also the students from different places to get encouragement to learn from one another across the country. So we want to thank the IQAC Cell for all its provision and all its encouragement to our department. Thank you, sir, once again. And now I would like to introduce you about our keynote speaker, Dr. Sanjeev sir. He is a professor and head of the department of Rajiv Gandhi University. Sir, very good morning and welcome you to this webinar program, sir. And I would like to give a short brief introduction about Sanjeev sir. He has been associated with the Department of Physics for the last 10 to 15 years. We are so happy that he has been always helping us in all our things with the Department of Physics in Rajiv Gandhi University. He has been a source of encouragement to us from the beginning. He is a very good teacher. He has been teaching as well as he's a very good researcher, doing research for the last 20 years. He has been, he's also a visiting faculty in many universities. He has published more than 50 publications in renowned and reputed journals, and he's also a peer reviewer in different journals. And words are not enough to tell him. He has been he has been supervising the students of PhD as well as MSc, and his research areas are including this simulation and fabrications of solar cells using 2D materials, and synthesis and characterization of second and sixth semiconductor materials. And he has also been working on the 2D languid thin films, and also the other field that he's working on is the charging, discharging properties of thin films for superconductors. He has been running a lot of projects also simultaneously, and he has been a member of many societies in different areas of different fields of physics. And he's a very source of encouragement for the Department of Physics. We have been really blessed by your presence today, sir. We are so thankful for accepting our invitation to give this keynote address to all the participants who have gathered here, sir. I will give the time for Professor Sanjeev, sir, for his valuable keynote address now. Thank you, sir.
Thank you, Jayanti, madam. Thank you, Dr. Jayanti. Respected Professor Dr. Modi, Principal of this college, Vice Principal, and IQAC Director Dr. Panda, all the physics department, faculty of the physics department, and my colleagues, students, and near future scholars of the physics. Today is the topic related to the innovation advancement towards the physics. What we have done in the physics in the last 100 years. I can say 100 years because the modern physics is started in early 90s. So that's the complete of the 100 years of the modern physics, you can say. When we are talking about the physics, we are talking about the science actually. The innovation in the science and physics, in the science and technology, we all combine, usually we combine the science and technology, but the innovation in the science and the technology is different, not the same. So on these lines, I would like to share my slides with you. It will be better. It's okay?
Yes, sir. You can share, sir.
I start with that 1,000-mile journey begins with a small steps. For any kind of the work, you have to be start first. That it will be complete. Without starting, no work can be completed. One of my professor told me, you have the two options. You have to create the two options. You just try. Then you try, you create the two options. Either this work can be done or this work cannot be done. So always try. So when you are taking the first step, you are not worried about what will be the end, but you have to try just. Now today, I was visiting one factory in so that one of the guys told me about that what is the relation between the you and me. It means he was the entrepreneur, I was a scholar. So he told me, you are nothing. We have a very good relationship between you and me. What kind of the relationship? You people, you are doing the conversion of the dollar into knowledge. And we are doing the knowledge into dollar. This is the vice versa. That's I wrote that, I kept that words, and I would like to share with you that this kind of way. Now, I start with the science. As I told you, the science and the technology has a great combination, has a great bond between both. The science is, if you are talking about the innovation in the science and if you are talking about the innovation in technology, the technology innovation is based on the innovation in the science. So always science comes first. That is the science and the technology, not the technology and science. Not the science, not the technology and science. Always science comes first and technology is better after that. You anywhere in the world you will say, but it's not a it is not a rule. It is a practice kind of thing. So science always first and technology always comes after that. The same line of that, if I talking about the hierarchy of the sciences. So you will see where everyone, in India especially, everyone, they want their children, for their kids, they want to take the admission in the science stream. Most of them is near about the 80 to 90% people are thinking about this type. And also that if you are talking about the which kind of the stream in the science, they always say the PCM, not CPM, not MCP. Always say the PCM. The physics comes first. I am not discouraged. I am sorry for that other people of the science if you are taking the other way. But the physics always, it is not a rule. It is just kind of a practice. Physics comes first and then comes chemistry. Always, when you see there's the another combination in the in the school and when you are taking the admission, that is the CBZ, not ZBC and not BGC. CBZ, the chemistry comes after the physics. So that is the, but how it comes, I will tell you in the last slides what will be the reason of that. But it is not a rule. I repeat that this is not a rule. It is a just practice, because it means the physics comes first, and after that the branches of the science comes later. And what do you mean by the science? If I talking about the science, what is the science? Science is nothing. It is the study of the systematical knowledge of any subject you are talking about. The science systematized knowledge derived from the observations, study of the experiments carried out in the order to determine the nature. The science means you can say we are trying to find out the mystery of that nature. A science must have predictive power. This is the important word when we are talking about the science. If you have not a predictive power, so that means science has failed. There is no science. Science must have a predictive power. Any predictions you can make on the basis of the science observations and scientific calculations. Now, what is the physics? You can say what is the physics? The physics is the first name is given by before there's the Galileo's times is the physics is the word, and first observation is given by the scientifically observation given by the Galileo. So originally the physics is natural science, and natural science or natural philosophy, you can say the science of dealing with the property of changes, of interactions. That means if there is an interaction, it will be change in the energy. So if the change is the flow of the energy, if there is a flow of energy, that means physics is involved on every phenomenon. If the flow of energy is flow when there is a change in the system. Is the two bodies or two kind of the objects is change their position, any kind of things, there will be a flow of energy. So that flow of energy with the respect to change of the system, that is known as physics. So physics like a mystery story, and the nature presents the clue. How can we go with the physics? The nature presents some clues, and we did the experiment on the basis of the clues, and we devised the hypothesis of that simple experiment and make a theory. And hypothesis predict other facts that can be checked in the right or wrong. If the theory is right, that keep checking again. If wrong, the new theory has been developed. And physics is an experimental science. We need some kind of the proof. We need any physics theory. It is not acceptable if there is no experimental evidence is there. Now, why is that's the motion? If I talking about the motion, a simple way, if the natural things, when I talking about the nature or natural things, is about the one word is represent the whole package. Is represent the whole package. So natural motion, I am talking about the like a falling body, object sits their natural place. Heavy body, heavy object, fast, fall fast, light objects fall slow, objects fall constant speed. So that's kind of a natural motion. But unnatural motions, when you are trying to find out the why is the unnatural motions, because the science, because of physics or any kind of the science is interested of the asymmetrical systems. We are very interested, the scientists are very interested about the unsymmetrical systems. So unnatural motions like a table pushed the moving body towards standing, still when force pushing it no longer acts and natural state of a body is in rest. Now, if I'm talking about the astrological physics or astrological physics was based on the logic, lot of physics is involved in if we are talking about everyone said it is a science, astrology is a science, but it's not exactly the science. It is not on the experiments, it is on the based on the logic. It provides a framework understanding the nature and illogical consistency. And it was wrong, who knows, or who can say, I cannot say it was wrong, but astrological physics rely on the logic, not on the experiments. So Galileo was the first experimentalist who measured that the height of the Pisa's the dome, and he gives that the idea how can you go to that's the experiment, how can you go to that's the science, next generation science, that is the observation. You observe and you abstract the things, and when you abstract the things, there will be you can conclude one kind of a hypothesis in your mind. And when the hypothesis in your mind, you can go to the predictions, and then predictions, and you can verify that predictions with the help of your experiments. So this is the phenomenon all the science we are doing, or especially in the physics. Our objective through the physics was to describe the process of the inquiry and the relationship. Describe the process of the inquiry and the relationship between the inquiry and the observations. What is the relationship between the inquiry and observations? So that you get some kind of the answers from that. When you develop that relationship between the inquiry and observations. Describe the difference between the matter and energy, as I told you, I described in beginning, and explain the relationship between a theory, a hypothesis, and an experiment, and describe how the scientific evidence used for the judge the truth of the nature. And there are the these fundamental aspects of the physics are that describe the organization of the universe as we are doing. The lot of physicists are involved to describe the organizations of the universe, and matter and energy also, that's describing the matter and energy, how the relationship between the matter and the energy, and understanding the natural laws that govern the universe. Believe that all even follow a set of the law that do not change. A set of the law of the universe, we have believed, we have fixed that laws cannot be changed, and reducing the applying natural laws and science as a process. Now, if I'm talking about the matter and energy, it is if you are not a physicist, so it is very interested for you, and if you are a physicist, it's also interested for you also. That if the matter, there is a liquid, solid, and gas. If you are talking about the energy, energy make the things can be changed. When you apply the energy in the matter, or it may be changed. The form can be changed of matter. When you apply the energy, form can and place of the body can be changed. It can be low, it can be go to the up when you apply the energy. And energy is in a different kind of the forms. As you understand, the universe consists of the only matter and energy. So that is the way we had divided the science here. That's the matter and energy. When you are talking about the energy, you are talking about the physics. When you are talking about the matter, you are talking about the chemistry. So that is the science is also is the fact that when you are talking about the science and technology, lot of confusion is created. The science is technology is also a science. No, when you have a problem, unsolved problem, you can go to the science. Science can resolve that problem, can give you the solution. After invention, after innovation, it can comes with kind of the solution. But when we are talking about the technology, the technology gives the service. Technology, the purpose of the technology only to give the service to service to the human being. The technology give us the you can say that's the it gives us the comfort to our life. So if that we are talking about the inquiry and observations, how the inquiry and observations can be the relationship can be fixed. The inquiry is that one kind of example you can take for the inquiry and observation. Inquiry, what is the relationship between the force and motion? The observation is that it takes more force to a heavy cart and it does not move a light cart. So that is the observations, and that is the inquiry, and that is the observations. So you can make one kind of a theory that inquiry is there is the valuable things are learned by the discovering the natural law through the inquiry, and it includes very practical knowledge. Once you know how the something generally work, you can oftenly figure out how to make it work for you, and you will learn to solve the real life problems. As I told you, the problems can be solved by the science, but technology only give the service. It can make the life, it can make comfort your life. Using that, how can you problem can be solved? The problem solution is especially for the students. How can you solve the problems and solving problem techniques? That is, for example, that if first step is determine what the problem asked you find out. Second steps, identify the information you are given. And third, identify law or relationships, can apply it and apply the given information and the relationship, and definitely you will find the solution. Importance of the experiment, because I have told you that the experiment, physics is an experiment science. We use the experiment to test the evaluate the theory. First, how the experiment is needed, that is the variables. It depends upon the variables. What kind of the variables you are talking about? When a ball is inclined from the top to the bottoms. And if you have a model, this kind of a model, you will see the distance and speed. You can make a graph between speed and distance and speed. But you have to be taking care of all the variables, and you can predict which centimeter, what will be the distance, whether you have measured or you cannot measure. So that kind of a prediction you can make on the basis of the experiments, and you can develop one kind of a theory. So scientific knowledge and the solar systems we have all, and if you are talking about the development in the solar systems, there will be a earlier civilizations believe that Earth was covered by a dome or which the sun, stars and planets moves. In the Middle Ages, the people thought that sun and stars and planets circulates the Earth, and today we know that the Earth and planets are round orbit the Earth, sun. So if you are talking about, as I told you, I will give you the last, how that the science is have the branch, the new branches comes in the science. First, is the fundamental particle and interactions of that is known as the physics. The interaction, we are talking about the interaction, there will be a interaction because of that's the energy between the two bodies. It may be a living body, it may be a non-living body, doesn't matter. But there will be interaction that will be known as the physics. But when the complexity is increase in the system, that comes to that particle are interacting and make one kind of another object that is known as the chemistry, and more complex interactions between the chemical molecules, and that's known as the biology. So that is you can say, that's why we can say physics, chemistry and math, or physics, chemistry and biology, and chemistry, botany and zoology. That kind of a system I have tried to introduce you. And in the last, I would like to say for every student that to remember that the poem of given by the Rabindranath Tagore, that's the when the sun went down in evening, he asked everyone on earth, who will take up my responsibility of providing lights? No one replied. A candle in a log cabin answered, my lord, I cannot light up the whole world as you do, but I will do my best to light up this small room. So with this message, I would like to say thank you very much for all the participants to give me this opportunity to speak here, and very, very best wishes for to success this program. Thank you very much.
Thank you very much, sir, for your elaborate keynote address. It was so wonderful to hear from you, sir. Sanjeev sir, Professor Sanjeev sir has really started his keynote address, starting with the natural science, and then he related that to the relevance of physics. And then he spoke about the inquiry-based study and its observation, which leads to the experimental physics. And also he talked about the problem-solving techniques and how important is the experimental physics, which solves many problems and leads to different theories. And also finally, he talked about the relationship between the physics and the other fields of science like chemistry, biology, and other different fields. Sir, your talk was really enlightening to each and every one of us. And you covered right from the beginning to the end and gave a brief description of this program. We thank you so much, sir, for your elaborate keynote address. I hope it was very useful to all the participants who have been hearing this wonderful talk. We thank you so much, sir, once again. Your encouraging words have been a real source of enlightenment to all of us, sir. We thank you for being with us today. And now I would like to give the time to the coordinator, Mr. Enoch Libang, for giving the instruction notes to the participants, how to go about this program. And also he will give the vote of thanks. And with that, the inaugural session for this morning session will be complete. So now I would like to thank Sanjeev sir, and I would like to hand over the session to the coordinator.
Hello. Thank you, madam. Is I'm audible? Good morning, everybody. So please check is I'm audible or not. Hello, is I'm audible? Okay. Thank you, madam. So good morning, all of you. So I am here to give the instruction for the participant. Participant, your audio and video will be automatically muted. And please, during the lecture, you can ask the question, but type in the Q&A section, in a question and answer section, or in chat section. You can ask during the lecture and after the lecture also. And there is a YouTube link given, live YouTube link given in your registered email and official WhatsApp group. So you can join us in the YouTube link also, in the YouTube also. And for the participant who is in the YouTube, they can type their question in the YouTube live chat, and we'll give the question to the respective esteemed speakers. And participants are hereby advised not to type any unwanted and unrelated text in the chat box and Q&A section. Thank you, and your attendance are available to us. And remember, there will be an attendance form will given during the lecture. So you have to fill up both the participant which are in the Zoom and which is in the YouTube. They have to fill up the attendance form. It will recorded as the attendance in this session. So thank you for that. This was only the instruction, and for a vote of thanks on the behalf of Department of Physics, I would like to start thanking our Principal Dr. Milorai Modi and our Vice Principal Dr. S.D. Chaudhary, sir, thank you for all the support, and both of you, sir, are the driving force of this institution, and you have always supported us. So thank you for that, especially our vice principal, sir, to taking some time, his valuable time, and deliver his speech in this program. So thank you, sir. And I would like my heartfelt thanks goes to Professor Sanjeev Kumar, sir. Thank HOD Physics of our parent university, RGU. Thank you, sir, for accepting our invitation as the keynote speaker. Thank you, sir, for that. And sir, your presence in our parent university, that is in the Rajiv Gandhi University, as HOD has blessed the university and the region. Under your leadership, the Department of Physics have developed in every sphere, and we are proud of you, sir. And I'm very looking forward to work under you, sir. And my big thanks goes to the IQSC coordinator, Dr. DP Panda, sir, for collaborating this webinar, 3 days webinar with us, and for your support, for your prompt response. Thank you, sir, for all of this. And my thanks goes to our department, our team, organizing team lead by our HOD ma'am, Dr. S. Jayanti, and our organizing members. And most importantly, my heartfelt thanks goes to all the participant who is participating this 3 days webinar. I hope, and I'm not hoping, I'm sure you will learn a lot from this webinar, and the outlook of the physics will be changed because of the speaker we have collected. And my thanks also goes to all the speakers who have accepted our invitation, and we are looking forward to hear from you all. So thank you, and thank you a lot. Thank you. Now the first technical session, first lecture will be start in 5 minutes. So please give us some time. So for ready. So thank you. So please wait for 5 minutes. Hello, Saurabh sir.
Hello. Hi.
Hello, Saurabh sir. I'm audible, sir.
Yeah.
Okay, sir. Okay, sir. Yeah, ma'am. Sir, you also audible?
Yeah.
Okay. Let me check first. Okay. Okay, participants. Our first speaker is Dr. Saurabh Bhattacharya. He's my big brother, my mentor also, and I'm very pleased to have you as our speaker, sir. And thank you for accepting our invitation. Dr. Saurabh Bhattacharya is presently working as assistant professor at the Department of Physics in Tinsukia College. He did his PhD in the field of complex plasma from the Department of Physics, Tezpur University. His specialization is theoretical high energy physics, and the area of research interests are to explore the physics responsible for the statistical properties in correlated systems like dusty or complex plasma, where the interaction and mechanism between the charged dust with the plasma background decide the phase behavior of the system, and hence responsible for the overall dynamic at the macroscopic kinetic level. He have many publications in the international and national reputed journal. And most importantly, sir is a very, very good teacher. I know him personally. He's like big brother to me. So he's a very good teacher, and I'm confident that student will learn uh, many things from him. And his topic is the beauty of quantum mechanics. He will talk on the quantum mechanics. Over to you, sir. Let
Thank
me.
you. Am I audible now?
Yes, sir. Yes, sir. You are audible, sir. You are audible, sir.
So a very good morning to all of you, especially the participants present here. So myself, Saurabh Bhattacharjee, and first of all, I would like to express my thanks to the organizing committee, the college fraternity, to invite me to share some of my experiences with the subject of quantum mechanics with you all. So it is always very nice to talk about physics, discuss about physics, and I am very happy to be here, be a part of this webinar. So without taking much of the time, I would like to start my talk. So my talk is the beauty of quantum mechanics. So all of you have heard about quantum mechanics. Some of you in your UG level have already learned what is quantum mechanics. So I will start from the very basic, and I will try to move the beyond quantum mechanics to some extent. Okay, so within this limited time, I will cover like this. So the first slide is a prelude, the development of classical physics. So it was the time in the late 19th century. So in the late 19th century, the classical physics was at its peak. Okay, the success of classical physics was at its peak. It was so successful, it was extremely successful, and people used to think that we have no new theory to be discovered. It is something we are at the periphery of completion. So whatever little we have to do the adjustment with the existing theories, and we can explain all of the observed phenomena. But at the same time, in the early 20th century, some dark clouds in physics came into being. Okay, so these dark clouds came mainly due to some experimental development in physics. When the experiment starts performing in physics, so Anu,
Yeah.
kindly when I ask you, then you will move. Okay.
Okay. Okay.
Okay. So when some experiments start developed in physics, and these experiments were inferring some of the phenomena which cannot be explained with the existing theories of classical physics, and we are in great demand or great need for a new theory, and that is the need based on which the quantum mechanics is developed. So next slide. Yeah. So this is the classical mechanics, and all of you know it comes from the Galileo to Newton, and Newton was the father of classical mechanics, and his famous equation F equal to ma was extremely successful to describe all of the observed phenomena in your day-to-day life. So this formula F equal to ma, it actually describes the dynamics of a system. Okay, for a given force, if you can solve the second order ordinary differential equation, you can easily figure out how the positions evolve with respect to time, and entire dynamics, entire phase space trajectory is evident to you. It was extremely successful. And then came a very famous prescription. It is the Euler-Lagrange equation. And this Euler-Lagrange equation is a famous equation in physics. It has been borrowed in quantum mechanics also, in quantum electrodynamics also, in quantum field theory also. It was an extremely successful prescription. And with this prescription, there comes the Hamiltonian formulation. With the Hamiltonian formulation, you can easily figure out the dynamical variable, how they evolve with respect to time. So in this way, classical mechanics were extremely successful, and they can explain at their time almost everything. The another part of the classical mechanics, next slide. Next slide, please. Yeah, it is the classical electrodynamics. It is the second beauty in classical physics. classical electrodynamics was an extremely successful theory which can explain the dynamics of charged bodies. Okay, so it starts with the Coulomb's formula, the very well-known Coulomb's law, then Biot-Savart's law, then Ampere's law, then Faraday's law of electromagnetic induction. The revolution just starts to begin. Then came the famous Lorentz, okay, the Lorentz formula, and then this is the person, James Clerk Maxwell, who can explain and who have actually combined all the laws of classical electrodynamics in a single framework, and with this he is able to describe the electromagnetic waves, the light. So it was the first field theory in physics, the first and foremost field theory in physics, the classical electrodynamics, which can explain the light. It was extremely successful, and in the last equation of the Maxwell dynamics, it is the Ampere's law with the Maxwell correction. Okay, and this brings this revolution, the Maxwell correction term, del cross B equal to mu naught into J plus 1 by C del E by del T. This del E by del T is the displacement current term, and this displacement current term has been added by James Clerk Maxwell, and this, because of the displacement current, the revolution came into existence. We can explain the theory of light. Then the next part of classical physics, next slide please. Yeah, it is the thermodynamics. Thermodynamics is always an extremely successful theory because there is no quantum version of thermodynamics. It is always thermodynamics, and it is a beautiful prescription you can use in quantum mechanics, also quantum phenomena also. With this description, you can describe the gross behavior of microscopic phenomena. Okay, suppose you have a cylinder, and this cylinder contains some amount of gas. So how can you say the cylinder having the gas are at thermodynamic equilibrium or not? Because we know the gas contained in a cylinder, typically it contains the Avogadro's number of particles. That means 6 into 10 to the power 23 number of particles. 6 into 10 to the power 23 number of particles are randomly moving in 10 to the power 23 random direction. Okay, so how can you figure out whether the gas is at equilibrium or not? This thermodynamics gives a prescription to figure out the thermodynamic equilibrium, and it says a temperature is the parameter which can explain or which can say whether a system is in thermodynamic equilibrium or not. Okay, so if you drop a thermometer in a gas containing the cylinder, if the thermometer say give you a single definite temperature, then you can say the entire gas having the 6 into 10 to the power 23 number of molecules are at thermodynamic equilibrium. Okay, a single temperature describing the gross phenomena of huge number of microscopic particles. Okay, this is the beauty of thermodynamics. It has been introduced many of the parameters like this. I have just mentioned one of the parameter, thermodynamic parameter, this is the temperature. The same formulation is borrowed into your black body radiation physics. In the black body radiation physics, thus gas is replaced with the radiation. A single temperature describes the entire spectrum. The entire spectrum, the entire energy distribution according to the wavelength is at the particular temperature. Okay, it is the temperature which decides the thermodynamic equilibrium of the system. This is the beauty of classical thermodynamics. Next slide. And here comes the last but not the least, the classical statistical mechanics by Ludwig Boltzmann. And this man has combined for the first time the thermodynamic with the statistical physics, and from here onwards the branch of statistical thermodynamics came into existence. If you see the last formula, the entropy is equal to k log omega. This omega is the statistical probability. Okay, this probability in the left hand side and in the in probability in the right hand side, and in the left hand side you have your thermodynamical property, that is entropy. So this is how, no, the previous slide. This is how you can combine the thermodynamics with the statistical physics, and how the behavior of the microscopic particle can be related to the macroscopic properties. For the first time, it has been introduced by this Boltzmann statistics. And it is it is much ahead of its time. This discovery is much ahead of its time. You cannot imagine how useful this discovery is. Next slide. Yeah, now all these that means classical physics that I mentioned you, the classical mechanics, the classical electrodynamics, the classical thermodynamics, and the Boltzmann statistical mechanics. Everything, when you combine, it was so successful, they can explain all of the observed phenomena. But the end of the 19th century, in the beginning of the 20th century, some of the dark cloud came in the sky of physics. And these dark clouds has been recognized by many of the physicists in those times, because these theories that I explained right now, these theories ruled in physics for 400, 500 years. And now the time came in the early 20th century, you have to discard those 400, 500 years beliefs. Okay, it is not a joke, because nobody wants revolution. If I told some of you that from tomorrow onwards your life will be different, you will not accept it directly, because you have been living like this for 25 years or 22 years, and right now somebody came and asked you that from now tomorrow onwards your life will be different, you have to adjust to that life. Nobody wants revolution. And same scenario was there in the classical physics also. The physical theories which were extremely successful for 400, 500 years, now the time came where to challenge those classical concepts, and the revolution needs to be done, but there is an inertia to get with the theories. So the first attempt was to preserve the classical theories and explain the observed phenomena. Okay, so this was the attempt, and this is very much obvious, because nobody wants revolution. These theories were so successful, how can we discard right present without having any difficulty, just reject the theories and accept the new theories? It is not a joke. Okay, so there is nothing new to be discovered in physics now, and all that remains more and more precise measurement. So this was the mentality of the physicists in those periods. Next slide. Yeah, the first dark cloud. The first dark cloud in the early 19th century and the late 19th century and in the beginning of the 20th century. The first one is the breakdown of the Galilean relativity. The breakdown of the Galilean relativity came from the Michelson-Morley experiment, which has been performed in 1887. These two American physicists, Michelson and Morley, they have performed an experiment and they have shown that velocity of light is absolute. It is same in all directions, irrespective of the motion of the source or motion of the observer. And this is something very much new to the physics community in those periods, because nothing is absolute in the universe. You know, in Galilean relativity, velocity is a relative quantity. The velocity that you measure from your rest frame is not the velocity that I measure from my moving frame. Okay, so this was the belief. But why the velocity of light is like this? Why the velocity of light is behaving in this strange way? There was no answer to the physics community. There have been many attempts by many physicists, but everything went into vain. Nobody could explain the beauty or the findings of the constancy of velocity of light or absoluteness of the velocity of light. And there came a 26-year-old boy from Germany without any profound physical background, raise his hand and say, I know the answer. He said, I have the answer. And he said, if velocity of light does not behave in this way, then the entire framework of relativity would have been destroyed. So velocity of light has to be behaved in an absolute way, otherwise the entire framework of relativity has to be destroyed. So what is the framework of relativity? The basic framework of relativity has to be preserved. What is the basic framework of relativity? The basic framework of relativity that all inertial observers are equally privileged to detect the laws of motion similarly, or laws of physics similarly. That means all inertial observers are equally privileged, because all the laws of physics that you observe in all inertial frame are same. This is the basic framework, or I can say in a common man language, the common man language version of the basics of relativity is that uniform motion does not allow you to detect the perceptible changes. When you are moving uniformly, you cannot detect the perceptible changes. So this is the beauty essence of relativity. And if you want to preserve this essence in electrodynamics, in Newtonian physics, in everywhere, you have to change the Galilean concept of relativity. And there came the Lorentz transformation and the physical insight of the Lorentz transformation for the first time raised by Albert Einstein. And that's why we consider him one of the genius in physics, because you can see in the latter part of my talk that he has contributed tremendously successfully in different aspects of physics. Where we need some bold step, this is the Einstein came first and took that bold step. He was an extremely genius physicist of all time. So first one is the Michelson-Morley experiment. The second one was the beautiful black body radiation, which have been an experimental observation, but there was no theory in the classical physics to explain the black body radiation. The black body radiation suffers from many difficulties. One of the difficulties is the ultraviolet catastrophe. And this is the person Max Planck this time came into being to rescue. But Max Planck even did not have the guts to propose the theory that light consists of particles. Okay, it was Einstein for the first time who put forward and say that it is the light which is consist of the branches of photons, branches of discrete packets of energy. Again, the Einstein came into existence. Einstein came into the picture with bold step. The next slide. Subsequently, the quantum physics has been developed in order to explain the phenomena which were not consistent with the classical physics. And unlike the theory of relativity, which is a single-minded miracle by Albert Einstein, quantum mechanics is not a single-minded development. Quantum mechanics has been developed time to time by many physicists, and some of them I have put in the picture. It is the Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Max Born, Louis de Broglie, Paul Dirac, and Richard Feynman. So they are not all. There comes the John Bell in 1964, gives a permanent stamp to the theory of quantum mechanics, or interpretational problem of quantum mechanics has been 90% solved with the discovery of John Bell. I am not going into details there. Next slide. And this is the experiment and ideas prior to quantum theory before 1913. Next slide. As I told you, the first blow of quantum, that means classical physics, came with the black body radiation. Okay, next slide. Now, this is the black body spectrum. In the x-axis, you have the wavelength. In the y-axis, you have the energy distribution of the wavelength. You can say the power density. It is the energy per unit volume. Okay, per unit time. That's why it is the power density, you can say. So it is the energy distribution according to the wavelength. And experimentally it has been obtained like this. But no theories in those period could explain the entire spectra. You can see the entire spectra. First, I think everybody, all of you know about the black body radiation. Okay, black body radiation is a thermal radiation. Thermal radiation means when you heat something, it radiates. Okay, it is the heating radiation. It is not the radiation coming from the electric spark. It is the heating radiation. And the beauty of this heating radiation, that this heating radiation is in thermodynamic equilibrium. Okay, so black body radiation is a temperature radiation at thermodynamic equilibrium. Now, this is the spectrum of the black body radiation in the right hand side corner. Okay, if you look at the spectrum of the black body radiation, you can see that at different temperature, the spectrum has been drawn. And the spectrum has a beautiful features. It has some peaks, and these peaks correspond to a particular wavelength at which maximum energy is being radiated. And as you increase the temperature, this sharp peak shifted towards the lower wavelength side. So these are some of the characteristics of the black body radiation. But with the help of classical physics, that means that mainly the classical thermodynamics and classical electrodynamics, they have been combined to explain this spectrum. But every time they have failed. One of the beautiful, that means attempt made by Winds and Rayleigh. Okay, both of them made their attempt, but both of them failed. Rayleigh could explain only the higher wavelength side, and Winds could explain only the lower wavelength side. So according to Rayleigh, if you move towards the, since he could explain only the higher wavelength side, so as you move towards the lower wavelength, according to Rayleigh, the power density rises sharply. Okay, and according to, and this again getting back to the decrease in power density with further decrease in wavelength could not be explained by Rayleigh. Similarly, Winds could explain the increase in the power density with increase in the wavelength, which is always there up to the peak. But after the peak, there is a decrease. But this decrement in the power density with respect to wavelength could not be explained by Winds. So both of them explain the both part of the spectrum, but the entire spectrum could not be explained by them. So it is a justified proof that their prescription of classical electrodynamics and classical thermodynamics is incorrect. And then came Maxwell, the Max Planck. Max Planck was a German physicist. He came and with some shaky ideas. I will not say it is a confirmed or bold representation of the quantum theory, but with some shakiness. Shakiness, why? Because it was the time 1901. Okay, in 1901, the existence of atom was not experimentally discovered. People even don't know that bulk material consists of atomic molecules. Okay, people did not have the atomic picture or atomic model in their hand. So how he could explain the spectrum in terms of quantum theory? So because he was also not sure about it, but he has explained it, and he has explained in such a way that he said the chambers of the black body radiation has the walls inside made up of some harmonic oscillator, and these harmonic oscillators, they absorb radiation from the black body, and when they emit radiation, they emit in a typical fashion. They don't emit continuously, but they emit in a discrete fashion, and they are emitting the radiation in discrete packets of energy having the value h nu. Okay, and with this some artistic picture, he could explain the black body spectrum with his old version. Okay, with his old Boltzmann statistical mechanics. Okay, and later on the famous our Indian physicist Satyendranath Bose have rejected his prescription and introduced a new picture to explain the black body spectrum, and there came the Boltzmann Einstein-Boltzmann statistic, Einstein-Bose statistic. Okay, Einstein-Bose statistics came into picture from that attempt made by Satyendranath Bose to explain the black body radiation when he was teaching his students at University of Dhaka. Okay. Now this Max Planck, he has made an attempt, and his intention was somehow I need to feed the car. So I need some formula, I need some prescription which can fit the car, and he has made it successfully. And this is the formula of the entire spectrum of the black body, which he could explain using quantum theory, considering that radiation consists of some discrete packets of energy. Okay. When Planck assumed that radiation consists of discrete packets of energy, he did not make it generalized, because he did not have the guts. He said that when radiation is emitted by the harmonic oscillator, they have been emitted in a discrete fashion. But he could not introduce firmly or surely that radiation in general consists of discrete packets of energy. It was Einstein who have introduced it in order to explain the photoelectric effect. Okay. So this is the beginning of the quantum theory, not quantum mechanics. Okay. With the explanation of black body spectra using the radiation emit in terms of packets of energy with this description. Now, second slide. So this is an information for the students. He was a German physicist who has formulated the equation of black body spectrum in 1900, and Wien and Rayleigh has developed the equation, but as I told you, they could explain only the two extreme parts of the black body spectrum, not the entire part. So Planck believed that this quantization applied only to the absorption and emission of energy by matter, but he did not have the guts to introduce that electromagnetic wave themselves consist of these discrete packets. Okay, so this is how he has introduced. Now next, the next thing came, the next beauty came with the experimental success made in the photoelectric effect. When radiation interacts with the matter, it is the photoelectric effect. And we all know photoelectric effect is a phenomena when light incident on a photosensitive material, the electron are ejected out of the material. Okay. And people have tried to explain it classically using quantum, using classical electrodynamics. And according to classical electrodynamics, if you want to explain the ejection of the electron with the incident light, it shows you that for ejecting one electron, when an electromagnetic wave incident on an electron in a photosensitive material, the time required to eject an electron is 100 years, theoretically, using classical electrodynamics. But practically, when we observe it experimentally, instantly electrons are ejecting out, and we are getting the photocurrent. So that theory failed, and again here came the Albert Einstein to explain or rescue us from this experimental anomaly. Next slide. And this is some of the history of photoelectric effect. In 1839, Edmund Becquerel observed the photoelectric effect via an electron in a conductive solution exposed to light. In 1873, the Smith, he found that the selenium is photoconductive. He has found some photosensitive material. In 1887, the Heinrich Hertz made observation of the photoelectric effect and production and reception of electromagnetic waves. In 1899, there comes Joseph Thomson, who investigated ultraviolet light is Crookes tube. Okay. In 1901, the Nikola Tesla, who received the US patent that described the radiation charging and discharging conductor by radiant energy. Okay. In 1902, the Philip von Leonard, who observed the variation in electron energy with light frequency. And Einstein attempted mostly in his explanation the number 6 discovery. Number 6 discovery in 1902, which observed that the variation in electron energy, when it came out from the photosensitive material, does not depend on the intensity of the light. It only depends on the frequency of the light. Okay, this is the important aspect of photoelectric effect. The variation of electron energy does not depend on the intensity of the light, but it depends on the frequency of the light. More energetic radiation you impose, more number of electron will come out. Okay, it does not depend how many photons you are applying to this photosensitive material. It depends on how much energetic the photons are. Okay, it clearly shows the light consists of packets of energy. So this is the famous Einstein formula in the photoelectric effect. All of you have, I think, studied it. In 1905, he has proposed this. Okay, and in the left hand side, it is the kinetic energy of the ejected photoelectron. In the right hand side, it is the energy of the photon minus the work function of the material. Okay, it is the energy to cross the barrier of the photosensitive material. Okay, it is known as the work function. Okay, so you can see that the kinetic energy of the electron directly depends on the frequency of the incident light, does not on the intensity of the light. So it is a remarkable finding and establishing the fact that light consists of packets of energy. And Einstein got his Nobel Prize for this, okay, to discovery of photoelectric effect. And 1916, Robert Andrews Millikan. Millikan was an extremely successful experimentalist. Okay, he finished a decade-long experiment to confirm Einstein's explanation of photoelectric effect. Okay, next slide. Okay, this is our famous Albert Einstein. Einstein sent this paper in Enil Dill Psychic. It is Physik, a paper in German language. It was in German, that means publication, with new understanding on the structure of light. Because you can see that this is the Einstein who have for the first time introduced the light consists of packets of energy profoundly, boldly in front of the physics community. Okay, he argued that light can act as though it consists of discrete independent particles of energy, in some ways like the particles of a gas. Okay, so his revolutionary proposals seem to contradict the universally accepted theory that light consists of oscillating electric and magnetic field, that is the electromagnetic waves. But Einstein showed that light quanta, as he called the particles of energy, could help to explain phenomena being studied by experimental physics. Okay, and since, as our Sanjay sir has told just before, that experiment has pursued it, because if experimentally the theory is not justified, you need to change the theory. Okay, so this is how experimental theory go hand by hand and developed in the later stages. Next slide. So now you can see the success of quantum theory of light came slowly and slowly. Next success came with the atomic structure proposed by Niels Bohr. Okay, next slide. Niels Bohr, he proposed the atomic structure of model, and that is popularly known as Bohr's atom model in 1913. And Niels Bohr got his Nobel Prize in Physics in 1922 for his explanation. And while considering or while formulating his Bohr's atom model, he has considered that the energy of the atom or electron inside the atom move in different energy levels, which are discrete, which are not continuous. Okay, in between two energy level, there is no any existence of the electron. Okay, so energy levels of an atom are discrete, not continuous. So he has quantized the energy of the atom, and in this way he has introduced the quantum nature of the radiation or quantum nature inside the atomic model. Okay, and he has successfully explained the spectrum of hydrogen atom, and he has told that when electron from a higher orbit jumps into the lower orbit, it ejects out the photons, okay, the quanta of light. And when electron from a lower orbit jumps to the higher orbit, it absorbs the photon. So in this way, he could explain the emission and absorption spectra also. And beautifully, he has formulated the energy of the hydrogen atom, which is minus 13.6 divided by n square. And he has also explained the emission and absorption, and it is the Rydberg's formula. You can see 1 by lambda equal to some constant 1 by nf, the quantum number of the final orbit, square minus 1 by quantum number of the initial orbit. Now this n, f and ni are the principal quantum number of the orbits of the electron. These orbits are nothing but energy level. Okay. So these energy levels are nothing but orbit. And he was partly successful because we know in the later stages, the energy expression of the electron in practical sense, it is not minus 13.6 by m square. There are other terms also. Okay, there are other terms, and these other terms could not be explained by Bohr, and these other terms is responsible for the fine structure of the hydrogen atom, which could not be explained by Bohr. And there came the Dirac. Okay, I will come to the later stage. Okay, fine structure of the hydrogen atom, which could not be explained by Bohr. It could be explained only when you impose relativity in quantum mechanics. If you cannot impose relativity with quantum mechanics, you cannot explain it. So quantum theory is slowly developing. Relativity is there in its form, but till now relativity has not combined with the quantum mechanics. So everything that I told you is based on the non-relativistic quantum mechanics. So this is the Bohr's atom model. Okay. So this is the electron transition that I told you. Next slide. Yeah. So this is the electron transition. So as I told you, Bohr was successful to some extent to explain the hydrogen spectra, but Bohr was also successful when experiment has been performed on the hydrogen spectra, and he could not explain the fine structure of hydrogen metal. And according to Bohr, electron move in certain particular orbits only. He said that electron moves only in discrete energy level. What is the background? So anything which rotates is accelerated, and when a charged particle accelerates, it radiates. Okay, so when electron accelerates around the nucleus, it will radiate because nuclear field is there. So in presence of a field, a charged particle is circulating, it will radiate slowly, it will lose its energy, and ultimately it should collapse with the nucleus. So Bohr's atom model is a primitive model. You can say it is a semi-classical model. It was not fully quantum model. It was mostly classical with some pinch of quantum theory. Okay, next slide. And slowly, the quantum phenomena has been coming into picture. Okay, and this is Louis de Broglie. He gets his PhD, and his PhD, because of this, he was a student of history. You know, Louis de Broglie. He was a history student, and what he did was a remarkable thing. And within one page, he wrote his thesis, and he got his Nobel Prize in 1929 for his discovery. Accidental discovery, you can say. So he said that all matter has a wave-like nature, and that wavelength and the momentum of a particle are related by a simple equation. So what he has said there, see, electromagnetic wave consists of photon. It has been formulated or has been established by Albert Einstein. But that is not the main striking thing, because anything which looks continuous is made up of some discrete object. It is very much obvious. You know, there is nothing to that means astonished about this, because water looks continuous, but it consists of water molecule which is discrete. It may be like that. In continuous, it is electromagnetic wave. When you zoom into, you may get the discrete packets of energy, which is photon. It is very obvious. What is very much striking is that these material particles, that means the discrete nature of the particle or these packets of energy also possesses an wave phenomena, or also possesses an wave characteristic. The reverse is also true, and this is very much striking. And this striking picture has been brought into existence by this man, de Broglie. Okay, and he named it as matter wave because it is the wave associated with the material particle. Okay, not only wave has the particle characteristic, de Broglie says that particle also have the wave characteristic, and this is very much striking. Why it is striking? I told you and you listened It is not like it is very simple. It is not that simple. I will tell you where the complexity, where the puzzleness is there in quantum mechanics starts with this. Okay, so material particle consists of some waves. So what he has said, he has simply take the two prescription of energy. One is developed by Albert Einstein, E equal to mc square, and for relativistic particle, you know, it is p square c square plus m naught square c to the power 4. Okay, for relativistic particle, this is the energy momentum relation, and we know this relation. Okay, it is the energy momentum relation of relativistic particle. And non-relativistic particle, the energy momentum relation is what? E equal to p square by 2r. Simple. But for relativistic particle, this is the energy momentum relation. The below one is the energy expression of the packets of energy, or the energy expression of the quanta. It is E equal to h nu, where nu can be written as c by lambda. He has simply combined these two and bring back a formula where lambda is equal to h, which is the Planck constant, divided by p, which is the momentum of the material particle. It is the momentum of the photon, because he has took the material particle being the photon. Suppose photon is the particle. Okay, because he has written it photon E equal to h nu, that's why it is the relativistic energy expression of photon he has taken into picture. So this general formula, root over p square. Okay, so this is for photon, and this is the momentum of the photon in the denominator, and in the right hand side, in the left hand side, you have the wavelength of the single photon. Okay, wavelength of the single photon, and this is known as the matter wave of the photon, because this is the wavelength not of the electromagnetic wave. It is the wavelength not of a bunch of photon. It is the wavelength associated with a single photon. That's why it is called the matter wave or de Broglie wave, and it is a quantum signature mark of any subatomic particle. Okay, any subatomic particle always respect the quantum mechanics, and they are always associated with the de Broglie wave or matter wave. Okay, anything which has a momentum associated with the matter wave. So this is the quantum signature. So this is the de Broglie hypothesis. It is called hypothesis because it is an hypothesis. You can say it is simply just relate and give the picture. Okay, next. Okay, this is the single photon interference. I will try to explain you from this picture, and from here onwards you can see why it is very much astonishing that material particles also have the wave character. Okay, suppose you have a double slit. Okay, Coulomb double slit, Young double slit. Suppose you have a Young double slit, and in front of the double slit you have a screen. Okay, and in the left hand side of the double slit, suppose you have a source of light. Okay, when source of light is allowed to pass through both the slits, all of you know that light as an electromagnetic wave, they will show you the interference pattern. Okay, so they are showing the interference pattern. Now we make the light source dimmer and dimmer. Okay, we make the intensity of the light source very low. So how can you make? You can make it with the technical ability, or you move the light source away from the slit. So as we know, the strength of the electric field is inversely proportional to 1 by r square. So as you move the source of light away from the field, away from the slit, the strength will be lower and lower. So somehow you manage to make the light source dimmer and dimmer and allow the light to pass through both the slits. And you will see that when the light is such a dim that at a time a single photon can pass through both the slits, you will get in the photographic plate the signature spots here and there, not the interference pattern. Okay, same light source at a higher intensity was giving you the interference pattern. This red interference pattern, can you see in front of the screen? This is the red interference pattern. This is from the light source. Now you make the light source dimmer and dimmer, and you make it dimmer and dimmer in such a way that at a time single photon can pass through both the slit. And with this prescription, you can see some spots on the photographic plate. You will not see any interference pattern. So this what infers? This infers that light consists of discrete packets of energy. Okay, just like bullet shooting the screen, you will get some of the spots here and there. It shows that light consists of discrete packets. It's okay. It has been established by Einstein. Nothing to worry about it. Now, what to worry about is this. If you allow the photographic plate to stay with such prescription for a long time, single photon are passing through both the slit, and you are allowing the photographic plate to stay there for a long time, you will see that eventually these dots grow and grow and grow and give you finally an interference pattern just like the wave. Are you getting my point? Okay, so with this prescription of the single photon passing through both the slit, at first you will get some of the spots. But if you do not remove your photographic plate and allow it to stay for a long time, you will see that eventually these dots will lead you to the interference pattern, which is a characteristic of the wave. Now the question arises. Previously, with the wave we are getting the interference pattern. Now, with the single photon, okay, passing through both the slit, because we make the light source such a dimmer, the particle characteristic of the light become much more prominent. Okay, we are getting some spots, is okay, this is the particle nature. But with this particle nature also, if we make them allowed to stand for a longer interval, we are getting the same interference pattern, which is a wave phenomena. Now the question arises whether a photon is a particle or it is a wave. Because in one hand, photon showing the characteristic of a bullet in the first slide of the screen, in the last slide of the screen, it is showing the characteristic of the wave. Now, what is photon actually is? This is the biggest question in quantum mechanics. Is it a particle or it is a wave? Quantum mechanics says that it is neither a particle nor a wave, or it is wave and particle simultaneously. But you can never detect it in its pristine form. That means wavical form. Wave particle at a time, you can never detect a photon like this. Then what is the answer given by quantum mechanics? Why you cannot detect the property of a photon at a time as a wave and as a particle? The quantum mechanics replied that because it is the act of your experiment which will not allow you to detect. So this is the interpretation of quantum mechanics to the abstract nature of the photon. So quantum mechanics explains photon, it is neither a particle nor a wave, or it is wave and particle as a whole. But we never see at a time the wave nature and particle nature of the photon. Every time we perform the experiment, we get only one of the characteristics. When we perform the photoelectric effect experiment, we get the particle characteristic of the light. When we perform the interference effect of the experiment, we get the wave nature of the light. So quantum mechanics says that it is the act of your experiment that is bringing the truth. Okay, so this is the biggest Copenhagen interpretation proposed by Niels Bohr and his colleague. Okay, so this is the interpretation of quantum mechanics which has been established till date and firmly with the discovery of John Bell in 1964, that this interpretation is the correct interpretation. If you accept it, accept it. If you reject it, go anywhere where the theories are as you like. Okay, if you want to accept quantum mechanics, you have to accept it with this puzzleness. So what is the puzzleness? Photon is neither a particle nor a wave. Then what is a photon? Photon is a particle. But if you allow me to pass the photon from both the slit for a longer interval of time, eventually it will give you the characteristic of a wave. Okay, because it is associated with the de Broglie matter wave. Okay, it is at a time a particle, at a time a wave, or it is neither a particle nor a wave. But practically you cannot see both the characteristic at a single time, because experimental will not allow you to do. It is quantum mechanics says that it's not my fault. Quantum mechanically, photon is neither a particle nor a wave. It is your experiment which is making the difficulty. It is the act of your experiment which is revealing the truth like this. Okay, so according to quantum mechanics, experiments not only finds the truth, it creates the truth. Okay, this is the interpretation of quantum mechanics. Experiment not only finds the truth, it creates the truth. Okay, so when you perform double slit experiment, you will only get the wave nature of the electromagnetic wave. When you perform the photoelectric effect, you will get the particle nature of the electromagnetic wave. So it is the experiment which is projecting the truth in different way in different situations. So this is the well accepted version or well accepted puzzle in quantum mechanics. Okay, thank you. Next slide. So this is the statement made by Richard Feynman. It is strange, but it works. With this strangeness, you have to accept quantum mechanics. And Richard Feynman said that's how it is. If you don't like it, go to a different universe where the laws are simpler. So this is a quote of Richard Feynman in 1979. Next. This is the famous Davisson-Garman experiment, and this has for the first time confirmed that material particles also exhibit the wave characteristic, because they have performed the experiment with the electron beam and they got the wave nature of the electron. Okay, and it has been confirmed that de Broglie hypothesis is correct. So not only wave has particle characteristic, particle also has wave characteristic. So when you do experiment, depending on the experiment, it will be evident to you which characteristic you are going to see. Okay, it is the act of your experiment that make it a wave or make it a particle. Otherwise, if you don't see it experimentally, it is wave and particle as a whole, or it is neither a wave nor a particle, some strange thing. You don't know it. Now, next slide. So this is the later development in quantum mechanics. So when quantum mechanics is developed with this interpretational problem, there are Max-Born statistical interpretation of the wave function that I will explain you. Matrix mechanics which is developed, wave mechanics by Schrodinger, and the heart of quantum mechanics, the foundation, the building block of quantum mechanics, the Heisenberg uncertainty principle. Then quantum mechanics has been related with the relativity by P.A.M. Dirac, the greatest mathematician for the century, P.A.M. Dirac. Then came exclusion principle and so on and so forth. Many things has been developed from time to time. Now, next slide. So I will, within a very small, that means effort, I am trying to explain you some of the postulates of quantum mechanics, because till now, before up to the discovery of your Bohr's atom model, it was quantum theory, it is not mechanics. But quantum mechanics has been developed in 1925 by Erwin Schrödinger and Werner Heisenberg. In 1900, they give the two different prescriptions to describe the mechanics of the quantum physics. Okay, mechanics. Mechanics mean what? I will tell you. What do you mean by mechanics? Because without mechanics, you cannot go further with the quantum theory. Okay, so the fundamental postulates of quantum mechanics, how to describe a physical state, how of the physical observable are being represented, what are the measurements, and how the physical states evolve with time. So these are the things you need to address. I think my dear friend Enuk have pointed me, I have 15 minutes, but I will take few minutes because I started at 11:45. Okay. So I think you can give me some more minutes because I was late with start. So fundamental postulates of quantum mechanics. So how is the physical state described? So how are the physical observable represented? What are the results of measurement, and how does the physical states evolve with time? So these are the fundamental postulates, and to address this, we need to prescribe a new mechanism. And the entire quantum mechanical formulation is mathematical. When you do the quantum mechanical formulation, there are few physics in it, and entire formulation is borrowed from classical mechanics and projected in a different way. Okay, I will tell you. So entire formulation is borrowed from classical mechanics and projected in a different way. The quantum mechanics is nothing but it is the mechanics in the linear algebra, and it has been developed in the Hilbert space. So Hilbert space is an n-dimensional vector space, just like your Euclidean space. Euclidean space is a three-dimensional vector space where the basis vector are I cap, j cap, k cap. Hilbert space is an n-dimensional vector space where the basis vectors are nothing but the wave function. Okay. So what makes quantum mechanics is the physical, that means makes quantum mechanics much more profound is the physical interpretation of the mathematical formulation and the results of them. Okay. So next slide. Next slide, please. Next. Yeah. So the heart of quantum mechanics. The heart of quantum mechanics is given by Werner Heisenberg with this formulation of uncertainty principle, which is popularly known as Heisenberg uncertainty principle. Heisenberg uncertainty principle will tell you the uncertainty in position at a given time and uncertainty in momentum at a given time at the same time is greater than equal to h by 4 pi or h cross by twice pi. Okay. So in the right hand side you have Planck constant, in the left hand side you have product of uncertainty in position and uncertainty in momentum. Dimensionally you have to match, because in the left hand side you have angular momentum dimension, in the right hand side you have the smallest value of angular momentum, which is the Planck constant. Okay. Now what it says, the definition of Heisenberg uncertainty principle is position and momentum of a subatomic particle cannot be measured simultaneously and accurately. So simultaneously means what? At the same mathematical instant of time, t naught. And accurately means up to what accuracy? Up to arbitrary accuracy. Okay. Whatever be your instrument you are using, whatever be the instrument that you are using, how much successful is your measurement procedure, uncertainty principle will be always there. You cannot erase the uncertainty. Okay. It is something, the intrinsic nature with which the particle can. Some music have been playing in the background.
Hello, sir. It's sorted out, sir. Sorry, sir. Sorry, sir. Panelists have unknowingly unmuted himself, sir. Sorry, sir. It's fine now. It's fine now.
Okay. Now the quantum uncertainty principle is the uncertainty in position and uncertainty in momentum is greater than equal to h by 4 pi. That means you cannot measure the position and momentum accurately simultaneously. Okay. Now any position, any momentum cannot be measured accurately or simultaneously. No. X component of position and X component of momentum cannot be measured accurately or simultaneously. You can accurately and simultaneously measure the x component of position with the y component of momentum. The uncertainty principle will not hold there. Okay, so uncertainty principle always hold in those cases where the pairs are canonically conjugate. Okay, canonically conjugate pairs. That means x component of position and x component of momentum. They cannot be measured simultaneously and accurately. Now, what is this del? This delta in the uncertainty? Is it something that error in the measurement or instrumentational error? No. This delta has nothing to do with the measurement, nothing to do with the precision of the instrument. This is something, an intrinsic uncertainty, which is nothing but the standard deviation. Okay, this delta is the standard deviation. This is the standard deviation. You just click once. You just click once, Enoch, Mr. Enoch, kindly click. Yeah. So this delta is nothing but this sigma x, which is nothing but the standard deviation. So standard deviation means what? How much it deviates from the mean position. Okay. So this uncertainty is nothing but the standard deviation. And what kind of standard deviation it is? It is a kind of standard deviation which cannot be erased with how many times you measure, with what precision you measure. Irrespective of that, this standard deviation always prevails. Okay, so this is the uncertainty in position and momentum. Now we know standard deviation is a statistical property. Okay, to get a standard deviation, you always need a distribution. So who will give me the distribution? The wave function is there in the quantum mechanics to give me the distribution to calculate the standard deviation. Okay, the standard deviation of position and standard deviation of momentum, x component of momentum, they will justify the uncertainty relation. And how you calculate it? You calculate it from the wave function. So when you do the measurement, what you will do to calculate the standard deviation in position and standard deviation in momentum, you have to make identically prepared system, and you have to simultaneously measure at all the system at the single time. So for each system, you will get a definite value of position and definite value of momentum. So ultimately, you will have a series of data for position and series of data of momentum. And then you calculate the standard deviation in position and standard deviation in momentum. And you put them in the framework, and you will see that a beautiful consequence. More the standard deviation in position is less, more the standard deviation in momentum will be bigger or higher. That means more precisely you measure the position, less precise will be the momentum. So this nature is very much intrinsic. It is already there to the particle by its birth. And this is the heart of quantum mechanics, the Heisenberg uncertainty principle. Okay, next slide. And this is nothing but the entire quantum mechanical formulation which has been borrowed from the classical mechanics. So in the left hand side you have classical, in the right hand side it is the quantum. So how the formulation varies? All the generalized coordinate in classical mechanics has been borrowed in quantum mechanics in terms of the operator. Okay, the dynamical variable in classical mechanics becomes the operator in quantum mechanics. That's like the position, momentum, energy. All these are becomes the dynamical variable in classical mechanics. When you brought them in quantum mechanics, they becomes operator. Now, how you measure in quantum mechanics? The measurement in quantum mechanics is that this wave function psi, as I told you, resides all the information about the particle. If you want to measure the position of the particle, mathematically, you have to operate the wave function with the position operator. In the right hand side, you will get a position eigenvalue corresponding to the position operator and leave the state unchanged. This equation that x acting on fx, suppose fx is the state of the particle, which has been described by the wave function in quantum mechanics. Because in quantum mechanics, wave function represents the state of the particle. So if you want to measure the position, the corresponding position operator has to act on the wave function which will give you a position eigenvalue, which is a measurement, and leave the state unchanged. Now, the canonically conjugate pairs in classical mechanics, they satisfy Poisson bracket relation, but in quantum mechanics, they satisfy commutation relation. Okay, and the Hermitian, the X and P, which is the Hermitian operator in quantum mechanics, they always give you the real eigenvalue. Only those operators are allowed in quantum mechanics which will give you real eigenvalues, because you are measuring, so it should give you some real value. So that's why quantum mechanics took only the operators which are Hermitian, because we know that Hermitian operator only give you real eigenvalues. Okay, now everything is okay. How to describe? Because in classical mechanics, either you solve Newtonian formula, or you solve the Hamilton equation of motion. If you solved it for an initial condition, for a given initial condition, you solve it, you can easily draw the phase space of the particle. That means at a later instant of time, how the position and momentum will evolve with respect to time, you can easily draw it. How you can draw it? You can draw it by solving the equation of motion. But in quantum mechanics, what is the equation of motion that is going to tell you how the particle will behave at a later instant? Knowing the behavior of the particle, or knowing the state of the particle means knowing the wave function psi. So knowing the wave function psi at the present time t equal to 0, how you can describe the wave function at a later time t equal to t second? And here the Schrodinger equation came into picture, which will give you the evolution of the wave function or evolution of the state. Okay, so this is the Schrodinger equation. I h cross del del t acting on the state will give you the total energy and leave the state unchanged. This is also an eigenvalue equation, because I h cross del del t is an energy operator acting on a state, give you the energy, which is nothing but the Hamiltonian, leaves the state unchanged. So this is the eigenvalue equation, and this is nothing but the Schrodinger equation. Next slide. So here I made some calculation. Okay, these calculations are being made to explain you what is measurement, actually what is measurement in quantum mechanics. So when you measure something, when you measure something in quantum mechanics, when you measure, you will definitely, for a single measurement, you will always get a single value. Okay, but in the next measurement in the same system, you may get a different value. So what you do, you prepare an identically prepared system, you do the measurement in each system. Suppose you want to measure the position of an electron. So suppose you have a system of a single particle, and in this system, you do your measurement and you find out the position. Okay, but if you allow the system to relax for certain time and do the second measurement in the same system, you will get a different value of the position. Okay, so every time you measure, you will get different value. Then you take the average and you say this is the average value of the position. So in entire quantum mechanics, nothing is deterministic. Everything is probabilistic. Whatever measurement you get in quantum mechanics is a probabilistic measurement. I give you an example. In hydrogen atom, all of you know, in the s orbit of the hydrogen atom, s orbit, the angular momentum quantum number value, the small l, is 0. Okay, the angular momentum quantum number value is 0. So when angular momentum quantum number is 0, the angular momentum of the electron will also become 0, because it is root over L into L plus 1 into h cross. So in the s orbital, when L equal to 0, angular momentum is 0. So when I say angular momentum of the electron is 0, how you explain it? Is it not moving around the nucleus, or is it stationary? So quantum mechanics says that the 0 value that you are getting for the orbital angular momentum of the electron in s orbital is not a precise value, it is a statistical average. Okay, since s orbital is spherically symmetric all the angular momentum has been added up vectorially and resultant angular momentum is 0. It is not that electron is not moving. Electron is moving, is resultant angular momentum is 0 because quantum mechanically you have taken the average of the angular momentum. So that is the reason. So how you do measurement? Suppose you want to measure any physical observable or dynamical variable A, okay, at a given time in a state defined by psi t. Okay, so what you do, every time you measure you get different eigenvalue. Suppose for the same physical observable in different measurement you have got eigenvalues lambda 1, in another measurement you get eigenvalue lambda 2, in another measurement you have lambda 3 dot 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 dot. So every time the state will be phi 1, phi 2, phi 3 dot 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 dot, different states, and these different states are the basis of the parent state psi t in the Hilbert space. Okay, now you can write the eigenvalue equation like this: operator A acting on any given state phi, okay, any given state phi, give you an eigenvalue lambda n corresponding to the state, leave the state unchanged. Okay, again, since the parent state psi t is a linear superposition of all the state, so parent state can be explained as a linear superposition of all the basis state, that is phi 1, phi 2, phi 3, phi 4 dot 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 dot. This is the picture, because in our Euclidean space our position vector r can be written at x I cap, y j cap, z k cap. This I cap, j cap, k cap are the basis vector, and you are expressing the vector r as a linear superposition of this basis vector. Similarly, in Hilbert space, you are expressing the psi vector as a linear combination of the basis vector phi. Okay. Now, when you operate this psi from the left hand side with the phi, you will get the probability amplitude of a given state. Okay. So when you do the modular square of this, you will get the probability that the system is in the state phi n at a given time. Okay. So the average value how you will get with this probability at a given state, and with the value of the eigen function that you are getting, that is lambda n is the eigenvalue of the physical observable. When you multiply it with the probability density, you will get the probability of measuring the value of the physical observable A in that given state. Then you add them up and you will get the expectation value. Okay. So this is how you can measure in quantum mechanics the values of the physical observable. Next slide. Next slide. I will skip this because this mathematics is not that much. And this is how to describe the particle in quantum mechanics using group velocity and phase velocity. You can skip it now. Keep it. Yeah. Now, so finally, everything that we have discussed till now is the non-relativistic quantum mechanics. But anything which is not relativistic is not genuine, is not practically useful, is not authentic. Okay, you have to insert the relativistic correction to get the real picture. Okay, there are many of the phenomena in quantum mechanics. Experimentally, they have observed Schrodinger equation, because Schrodinger is a non-relativistic equation. So, to explain those of the phenomena, you have to make the Schrodinger equation a relativistic equation. So, for a particle physics, also we need a relativistic formulation of quantum mechanics. The first take a few moments on the review of the quantum non-relativistic quantum mechanics. So, as I told you, the equation S1 is your Schrodinger equation. Okay, free particle Schrodinger equation where potential is equal to 0. Okay, so it is minus 1 by h twice m del square phi I del psi by del t. Now, this Schrodinger equation is not Lorentz invariant. Lorentz invariant means if you make the Lorentz transformation to this equation, you will not get the prescription of this presentation of this Schrodinger equation intact. Okay, so it is not preserved under Lorentz transformation. That's why it is not Lorentz invariant. Okay, so you have to make the Schrodinger equation Lorentz invariant to make it relativistic. So let's start it. Next slide. Next slide. So the Klein-Gordon equation, this equation is the relativistic version of this Schrodinger equation. It is the simple relativistic version. I think all of you have gone through your relativistic electrodynamics or 4-vector notation. So I can easily give you the picture of the Klein-Gordon equation. So Klein-Gordon equation is the equation number Kg3. Okay, Kg3. So this equation number Kg3 is the Klein-Gordon equation format. Okay, and this is the relativistic Schrodinger equation. So it is nothing but you insert the relativistic prescription by using the 4 momentum, okay, and the 4 derivative. This is the D'Alembert's operator del mu, and you will get the description of the Klein-Gordon equation in terms of relativistic correction. Okay, it is del mu plus m square psi equal to 0. This is the free particle equation. Okay, there is no potential. Now look at this equation. This del mu covariant and del mu contravariant, this is known as the D'Alembert's operator. It is also written as del square, that means box del, like a box. Okay, I have not written it here, but it is like a box. It is the representation of contravariant. Unlike your Schrodinger equation, if you see your Schrodinger equation is first order in time derivative and second order in space derivative. But this Klein-Gordon equation is both second order in space and time derivative, and you make it covariant. Okay, covariant means which is relativistically invariant. Okay, now this is very good, but it has some problem, and the problem is that since Schrodinger equation is relativistic, the energy momentum relation is equal to your E square equal to P square plus m square. Okay, energy momentum relation is equal to E square equal to P square plus m square. Okay, so if you take the modulus of this energy, you will get plus minus root over P square plus m square. That means energy can be both positive and negative. But since this Klein-Gordon equation in explaining a single particle equation, because quantum mechanics is always a single particle mechanics, it is not a multi-particle mechanics. Okay, when I write Schrodinger equation always describes the equation of a single particle. Okay, now this quantum mechanics, this Klein-Gordon equation is also an equation of a single particle, which is a relativistic particle. Okay, how the energy of a single particle can be negative? Energy cannot be negative. We always know energy is positive. So to be simple, this Klein-Gordon equation could not explain the negative energy. Another problem is the probability density, which we know that psi square, modulus psi square is the probability density. So what it gives you the probability of finding the electron per unit volume. In case of Klein-Gordon equation, in the next slide please. Yeah, in case of Klein-Gordon equation, the probability density rho, okay, is not always positive definite, because you know it is rho is not psi star. Here it is I psi star complex conjugate psi multiplied with the time derivative of psi minus psi multiplied with the time derivative of complex conjugate of psi. Okay, so there is a minus sign, and since psi n is first derivative in Klein-Gordon equation can be arbitrarily chosen as an initial value, because it is a second order differential equation. You can choose psi and psi del psi by del t as an initial value arbitrarily, you can always have a possibility that your this density rho has to be negative. So probability density can never be negative because probability of finding the particle can never be negative. So these are the two problems faced by Klein-Gordon equation. When you try to explain Klein-Gordon equation to explain the dynamics of a single particle, which is relativistic. Okay, these are the problems faced by the Klein-Gordon equation. Now, this Klein-Gordon equation, if you say that this is not the equation describing the dynamics of a single particle, it is the equation describing the dynamics of a stream of particles, or it is the equation which dynamics describe the dynamics of a field, then this problem can be erased out. Okay, so this is the first time there came an intuition or inference that when you make your Schrodinger equation relativistic, you are no longer in the field of description of a single particle. Okay, you are entering in the description of a field or a multi-particle system. So Klein-Gordon equation can be successfully interpreted when you say that psi is not the wave function of a single particle which is relativistic, but it is the wave function of a complex scalar field. Okay, that time it is not called wave function, it is known as field function. It is the field function of a complex scalar field. If you can say this, I can show you that this negative probability density and negative energy state problem can be solved. So Klein-Gordon equation is the first field theory picture in quantum mechanics. Next slide. So here the final slide or final topic that I am going to cover, the Dirac equation. This Dirac, PAM Dirac, for the first time came into being to describe or rescue us from the difficulty faced by the Klein-Gordon equation. Dirac has pointed out one thing. Dirac has pointed out one thing there. Why I am getting the negative energy state problem in Klein-Gordon equation and why I am getting the negative probability density problem in Klein-Gordon equation. The reason is that the Klein-Gordon equation is second order in time derivative and second order in space derivative. So Dirac made an attempt to write an equation for a relativistic particle, okay, which is first order in time and first order in space. Okay, and with that it satisfies the energy momentum relation, E equal to root over p square c square plus m naught square c to the power 4. Now what Dirac did, second slide. So the first equation is the Schrodinger equation that you all know. It is first order in time in the right hand side, second order in space in the left hand side. Second one is the Klein-Gordon equation. It is the first order in both time and space. Dirac made an attempt to formulate an alternate theory of Hamiltonian where the energy and momentum relation has been preserved, as well as the equation being the first order in both space and time. Okay, so what did he multiplied some arbitrary constant alpha and beta before the momentum value and the mass value and write it in the first order form. See, here I am not writing your psi equal to p square by twice m. Okay, not p square c square. C square I made 1 by natural unit. I am not writing your E h psi equal to p square plus m square, which I have written in the case of Klein-Gordon. Move back 2 slides before. Kindly move back 2 slides before. Another one. Another one. No, 2 slides before. Back. 2 slides back. Two slides back. 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 Yes. See, in the Klein-Gordon picture, I have written E square equal to P square plus M square. Okay. So in place of E square, replace E with the energy operator. It is del square by del T square, and P square is replaced with the momentum operator. It is del square psi. Now you come to Dirac equation after 2 slides. Next slide. Yes. Now you see the Dirac equation H psi equal to not P square, it is alpha dot T. So I make the momentum operator first order in space and not M square, it is M. So I multiply some arbitrary constant alpha and beta with them to make it intact. Okay. So let's start with this. Now my job, the Dirac job, is to find this, the value of this arbitrary constant alpha and beta. So with the equation D1, if you expand it, you can say in the component wise, if you expand in Px, Py, Pz format and replace them with the operator representation, you will get this relation. Okay, with this relation. And eventually in the next slide, this next slide, solving it, you will get the nature of the constant alpha and beta in the equation D2, D3 and D4. Look at the equation D2, D3 and D4. Just doing simple calculation, you can easily figure out what should be the nature of alpha and beta. See, alpha x square, x component of constant alpha, y component of constant alpha and z component of constant alpha and beta, their square should be equal to 1, and the j component of alpha multiplied with b and b multiplied again with the j component should be equal to 0. This is not the anti-commutation relation, because we know in the commutation relation xp minus px equal to 0. It is like xp plus px. That's why it is called anti-commutation. Okay. So these are the condition has to be satisfied by alpha, and it can immediately say you, because alpha has 3 components. Okay, in 3 direction, along with them they are satisfying the anti-commutation relation, so there cannot be number. So only thing there should be matrices. Okay, so alpha and beta should be matrices. Now my Dirac job is to find out what type of matrix should satisfy this condition D2, D3 and D4, and he has find out that it is the Pauli spin matrices are there which will satisfy this condition. Okay, next slide. Okay, so it is the Pauli spin matrices. In the exam lower side, you see sigma x, sigma y, sigma z. These are the 3 Pauli spin matrices which can easily satisfy those conditions: alpha x square, alpha y square, alpha z square equal to 1, and alpha I beta plus beta into alpha I anti-commutation relation which is equal to 0. Okay, these 2 conditions can be easily satisfied with this relation, and if you take beta as an identity matrix. Okay, using this prescription, he has represented alpha in terms of Pauli spin matrices and beta in terms of unit 1 0 0 minus 1. Okay, so using this, he can explain the representation of the constant that he has used to make the first order position and time equation, which is nothing but the Dirac equation. Okay, he has bring out this constant successfully, and it is a great success. You know why it is a great success? Because it is for the first time theoretically bring out the prescription of the electron spin. Before the Dirac equation, spin has been introduced on ad hoc basis. There was no theoretical prescribed description of the spin. It has been introduced by hand where it is necessary. But it is the Dirac equation, which is a relativistic equation for the electron, which has shown you that when you demand relativistic invariance of an equation, when you demand the relativistic invariance of Dirac equation, spin comes automatically as a byproduct. So it is the physical basis of the spin of the electron. Okay, so it was an extremely successful theory. it has bring into picture the existence of electron spin. The next slide. With my limited time, I will just show you how the negative energy state problem and the negative probability density problem faced by Klein-Gordon equation has been worked out in Dirac equation. So if you do the same, this is very simple. Okay, don't you confuse with the symbols. This is very simple probability density calculation. Okay, probability, that means equation of continuity calculation. You just go in this way, and in the next slide. Yeah, in the next slide, you can see that unlike your Klein-Gordon equation, your probability density rho, which was in the Klein-Gordon equation, what was the expression? It is psi star del psi by del t minus psi del psi star by del psi. So there is always a tendency that rho will be negative. But unlike that, Dirac had successfully point out or rescue us from this negative probability density problem, and he has showed that it is psi star into psi. Okay, it is always positive definite in the next where rho is always greater than 0. So what are the inference? Unlike the Klein-Gordon equation, Dirac equation has probability density which are always positive that we need. The second is, in addition, the solution to the Dirac equation has the 4 component of Dirac spinor, because spin has been automatically come in the Dirac equation. So the wave function becomes a 4 component wave function. We call it a spinor. It has 4 components: psi 1, psi 2, psi 3, psi 4. Okay, a great success of the Dirac equation is that these components naturally give the property of intrinsic spin of the electron. Okay, as I told you, and with this spin you can always explain the intrinsic magnetic moment of the electron. So all these were not there in the non-relativistic Schrodinger equation. Next slide. So this is the beautiful D9 equation, D9 number equation, which is the covariant form of Dirac equation, Lorentz invariant form of the Dirac equation. Okay, now next slide. So these are the properties of the gamma matrices. Okay, gamma matrix I have used. Gamma matrices are nothing but multiply your alpha matrices with some values. Okay, I have shown you how gamma matrices in the previous slide. You just go in the previous slide. Back, you just yes. So you see this gamma naught equal to beta. I have written beta equal to gamma naught. This gamma 1 is nothing but beta into alpha x. Gamma 2 is beta into alpha y. Gamma 3 is beta into alpha z. With this formulation, I have point out this covariant form of the Dirac equation, D9. Next slide. So these are the property of the gamma matrices. Okay, and this property easily satisfied the property of the alpha and beta matrices. Okay, next slide. Next slide. Now this is the last slide, and using this slide I will explain within 5 minutes how to describe or how to apply Dirac equation for a free particle. There is a reason why I am doing it, because using Dirac equation, what are the successes? Probability density is always positive. Spin come automatically as a byproduct of the Dirac equation, but the negative energy state problem still not addressed. Okay, now using this I will say you the existence of the negative energy states, how it has been rescued in Dirac's prescription. Okay, so this is the first equation. This equation is nothing but the free particle solution of the Dirac equation. Okay, so for a free particle, that means I am right. For free particle means what? The potential is 0. Now I consider this particle is not only free but also it is at rest, so its momentum is also 0. So when you give the momentum equal to 0, the solution of the Dirac equation become like this, just before D10 in the denominator. in the ekdam lowermost portion of the slide, you see the solution of the Dirac equation for a rest particle is psi equal to u as a function of energy and 0, where momentum is equal to 0 equal to e to the power IET. This is an stationary state equation, as we know, of a definite energy E. Okay. Now, when you apply this solution to the Dirac equation, you will end up with the equation D10. That means E gamma naught U minus mu. Next slide. Yeah. When you solve this equation beautifully, when you solve this equation, you will see that you will have 4 orthogonal solutions, because it has 4 spinor, psi 1, psi 2, psi 3, psi 4, and you will get 4 orthogonal solution U1, U2, U3, U4. Out of the 4 solution, U1 and U2, they have energy E equal to plus m. That means energy cannot be m, it is mc square, but c can be taken as unity. C can be, you can write c equal to 1 in natural unit. Okay, so everywhere I am writing E equal to m, by default it is E equal to mc square. So 2 solution have a energy equal to mc square, and another 2 solution have an energy equal to minus mc square. Okay, so these 2 solutions, the first 2 solution where energy is positive, are the 2 solution for both spin up and spin down, and second 2 solution where energy is negative also have spin up and spin down. Okay, so Dirac has interpreted 2 spin of the electron using 4 solution and 2 energy positive and negative. Okay, so psi 1 and psi 2, both of them represent 2 spin states. Okay, plus up upward plus z direction, minus up negative z direction, 2 solution, and these 2 are in the positive energy state. Another 2 solution, plus up in the z, minus up in the minus z, and these 2 spin state in the negative energy. Okay, now how Dirac interpret this negative energy? In the slide, next slide. So this is Dirac's famous interpretation, beautiful interpretation, much ahead of his time, and you can see how much he could anticipate. You will get, that means, astonished with his anticipation, how beautifully he is anticipated. So Dirac has model like this. Dirac has proposed a model, it is known as Dirac C model. Okay, so according to Dirac C model, the entire universe is filled with Dirac C. Okay, so inside the C, you will have the negative energy electron, and you cannot see those electrons, and the electron that you detect experimentally is outside the C. Okay, that means in the positive energy state. Okay, so when an electron jump from a negative energy state, which is nothing but inside the C, and he has said that it is the vacuum. Okay, vacuum means emptiness, and in the bed of the emptiness, you will have the negative energy electron. So Dirac for the first time proposed the idea that the vacuum is not completely vacuum, it is also filled with something, and Dirac said that it is filled with the negative energy state of the electron. Okay, now this negative energy state of the electrons, when they jump to the positive energy, there is a hole created. Okay, in the second diagram you see there is a hole created. Okay, in the third diagram, and how this hole is created? This hole has been created when an electron in the negative energy jumps to the positive energy. So how it will jump? It will absorb a gamma photon and it will jump from negative to positive. So how much energy it has to overcome? It has to overcome 2 mc square energy, 2 mc square, because plus mc square in the first, minus mc square in the denominator. If it had to overcome this barrier, we had to overcome the 2 mc square amount of energy. If gamma photon has an energy greater than or equal to 2 mc square, it can create electron and anti-electron pair. This anti-electron finally has been experimentally detected, and it is a triumph or victory of the Dirac proposal or Dirac theory. Next slide. And this is the discovery of the anti-electron. It is known as positron. Okay, it is the positively charged electron, because Dirac say a hole will be created because from anywhere where a negative particle will come out, a positive charge will definitely resides there. So Dirac interpreted as the anti-electron. This anti-electron is nothing but the positron, or Dirac says that it is the electron hole, and it is nothing but the positron, which has been described by C.D. Anderson in 1933. And this provided a verification of the prediction of the Dirac equation. How beautifully Dirac has predicted the existence of antiparticles. For the first time it came into existence. So see, once you incorporate relativity in Schrodinger equation, so many things automatically came into existence. So many things. That's why relativity and quantum mechanics, the two pillars of the modern physics, why they are so important. Next slide. Next slide, please. So when Dirac has proposed, next slide. Before that. Yeah. So this is the final Feynman interpretation of the antiparticle, because Dirac has proposed it as the electron hole or anti-electron having negative energy. Feynman has said that it is not anti-electron with negative energy. You can interpret it as a positron with positive energy, and it is nothing but a new particle that you can detect. It is not that you cannot detect. It is inside the sea. It is something that you can detect, that has been detected by Anderson, and Feynman beautifully has proposed, Feynman and Stuckberg, they have beautifully proposed the equivalent picture of antiparticle with a more profound description. He has said that it is not negative energy electron, it is the positive energy electron, which is nothing but a positron. Okay, so this is for the first time, this is the most well accepted description of the antiparticle of the electron, which is nothing but the positron. And in the right hand side, you can see the famous Feynman diagram. It is the pair creation diagram. Okay, how pairs have been created, pairs have been annihilated. As I told you, 2 mc square energy when you incorporate in a medium, from vacuum the electron positron pair can come out. Thank you. Next slide. Thank you.
Hello. Thank you, sir. Thank you for your excellent, sir, excellent and simplified explanation on the beauty of quantum mechanics. Thank you, sir. And sir, due to we have lots and lots of queries for you, but due to time constraint, I will take some of the question. So this is a
I
question.
can address the question later also by email.
Okay. Yes, sir. Yes, sir.
Send it to me.
Yes, sir. I have a question from Amit Tiwari. He asks, sir, light shows dual nature. In
Yes.
interference, we study light as a wave.
Yeah.
Sir, my question is, we can study the interference by using only the particle nature of light. The question is, can we study the interference by using only particle nature of the light?
Yes. See, this is, once you enter into the domain of quantum mechanics, you have to remove your classical thinking. Okay, once you enter quantum mechanics, you have to remove your classical thinking. You have to remove the cap of classical mechanics. If you cannot remove the cap of classical mechanics, you cannot digest quantum mechanics. Okay, so as I told you that wave and particles simultaneously you cannot detect. Okay, when you do the experiment, either you detect the wave property or the particle property. And the question that he has said that using particle nature, is it possible to describe the interference? Yes, because when you allow the single photon to pass through both the slit, okay, you are allowing photon one by one to pass through both the slit. So for the initially the photons strike the screen here and there, but if you allow the screen to stay there for a very long period of time, eventually the interference pattern has been developed. So this shows that the particle nature also shows something that is the signature hallmark of the wave characteristic, because we know that interference can only be created by wave, but here you can see that particle nature of the light also creating the interference phenomena. So particle also have the wave nature.
Okay, thank you, sir. One of our student, Jain College student, had asked, "What is the physical significance of eigenfunction or eigenvalues? What is the physical significance of eigenfunction and eigenvalues?"
Yeah, see, eigenfunction is nothing but the state of a system. Suppose in classical mechanics, how you describe the state of a system? In classical mechanics, when somebody asks you what is the state of a system, how you describe? You just draw the phase space trajectory. Okay, that decide that this is the state of a system. At each point on the phase space trajectory, you will have a definite momentum and definite position at every time. Okay, so every time you will have a definite value of momentum, definite value of position. So this is the state of a system. In quantum mechanics, the state of a system is described by an eigenfunction, which is nothing but psi. Okay, this psi represents the state of a system. So it is known as eigenfunction. Now eigenvalue is the value of the physical observable that you are interested to measure. Suppose you are interested to measure the energy in that state. So my state is at the state psi. I am interested to measure the energy. So what I will do, according to the mathematical prescription of quantum mechanics, I will operate the state with the corresponding energy operator that will give me the eigenvalue. That means the value of the physical observable that I am going to measure. Okay, leave the state answer. So these are the physical significance of the eigenfunction and eigenvalue. Eigenvalue is nothing but the value of the physical observable, and eigenfunction is nothing but the state of a system.
Okay, thank you, sir. I'm taking a last question, sir. This is from Himen Chamwa. He asks, "Sir, what is the dimension of wave function?"
See, wave function has some properties. Any function cannot be a wave function in quantum mechanics. The first thing, wave function has to be single valued. Wave function has to be, second thing, wave function has to be square integrable. Third thing, wave function should be analytic. The fourth thing, wave function should get vanished at the boundary. These four conditions has to be satisfied to be a suitable wave function in quantum mechanics. Now, if you ask what is the dimension of quantum mechanics, dimension of wave function, if you are interested to describe the wave function of a free particle, then the dimension of wave function is the dimension of the free particle. That means it is minus infinity to plus infinity. If you are interested to describe the wave function of a particle within a box, then dimension of the wave function is dimension of the particle within the box. It is the length of the box. So it depends on what situation you are facing. Okay, thank you.
Okay, thank you, sir. We have a lots of question and queries, sir. Participants, my dear participants, Dr. Saurabh Bhattacharya sir is a very, very student-friendly teacher. So definitely he will answer all your queries. Sir, if you don't mind, I can share the email, your email to the WhatsApp group,
Yeah,
sir.
it's
Okay,
okay.
sir.
Just
Okay. Okay. Thank you, sir. Thank you, sir. Or
thank you, thank you.
once
I
again,
also
thank you, sir.
thank Anup for cooperate with me. Thank you, thank you, thank
Thank
you
you, sir.
all.
Sir,
Thank
it
you.
was a lovely session, sir. So thank you. Thank you very much. And thank you for accepting our invitation, sir. Thank you.
Thank you. Thank you. It's my pleasure.
Okay. So, my dear participant, now we'll come to our second lecture of the day. Uh, so, let me connect first. Give me 2-3 seconds. Okay. Our sir is ready. Hello, Anup sir.
Yeah,
Is I'm audible?
yeah, yes. Am I?
Yeah. You're audible, sir.
Yeah.
Okay. Dear participant, this is our second lecture. He is Dr. Anup Kumar Nath. He's my friend. He is also a very a student friendly. He's teaching mainly based on the how he want to connect with the student. He loves to connect with the student. He's a very student friendly teacher. So Dr. Anup Kumar Nath is presently working as assistant professor at the Department of Physics in the Cotton University, Guwahati, Assam. He did his PhD from Tezpur University. His specialization is on condensed matter physics, and the area of interest are polymer, polymer electrolyte nanocomposite and nanocomposite for the energy storage application. He have many publication in the international and national reputed journal. So I'm sure, my dear participants, you will learn a lot from our Anup sir. So sir, it's all yours,
Yes.
sir. Sir, you can
Yeah.
share
Okay.
the screen, sir.
Okay. First of all, thank you very much to Jain College. Uh, Thank you very much to my friend Anouk, and I hope the students will enjoy my talk. Generally, I like to connect with the students, and I like very general talk. And I hope they will ask me questions and they will enjoy. So I am going to share my screen. Anouk, is it visible?
Yes. Sir.
Okay.
Yes, sir. It's visible.
Okay.
Yes, sir. Yes, sir.
Yeah, thank you. So in today's talk, I'm going to talk about the paraphernalia of physics in nanotechnology. Basically, I have given my email also here, anup.tu@gmail.com. So you can ask me questions or you can contact me for anything. So why I have chosen this topic, that is nanotechnology. So our present generation is that it's a new revolutionary technology. So as Dr. Alan Bromley has said, it is the sixth revolutionary technology introduced in the modern world. We can say that there are different revolutions. In 1700th centuries, there are industrial revolution. In 1940s, there are nuclear energy revolution. Then in 1950s, we have silicon revolution. And because of this revolution, we are using our connected devices, laptops, and anything, this kind of electronic devices. In 1960s, we have green revolution, and that is the agricultural revolution. We got many techniques in agricultural industry. And in 1980s, we have some information technology revolution. From 1980s, we are very much effective in transforming the information in our within ourselves. Then in 1990s and 2000s, there is a development in nanotechnology and as well as biotechnology. So basically, it's a truly revolutionary technology. And we have to understand what is nanotechnology. And for that, basically, it is a very interesting topic so far, I think. And let's, for students, we start from a clip of a movie that I think all of you have enjoyed this movie. I think you will not hear the voice, but it's Iron Man. And you can say that when he's going to save the world from some people, and he's coming in a suit. So when his friend asked where did it comes from, then Iron Man said, it's nanotechnology. You like it? So it's nanotechnology. So the suit he is using, it's from nanotechnology. So nanotechnology can do much beyond our imagination. But basically it's a future technology. Nowadays we are not so advanced to go up to that level. But for students, we should know what is nanotechnology. So basically in this talk, I would like to answer 3 basic questions of any science topic. That is what, why, and how. So first we'll tell about what is nanotechnology. Then we said why nanotechnology, and then we'll try to understand how nanotechnology, how we are using technology in nanoscience. So what is nanotechnology is that it is the understanding and control of matter at dimension of roughly 1 to 100 nanometers. And 1 nanometer is quite very low. This is a table where I have given that 1 nanometer is 10 to the power minus 9 meter, or 10 to the power minus 33 micrometer. So nanotechnology, it's very less. So the term nano actually comes from a Latin word, vono, like that. So its meaning is dwarf. So it's small. Nanotechnology means it's small. And the technology of nanoscience started by the famous physicist Richard Feynman. And when he said in 1959 that there is plenty of room left at the bottom, that means where we see the bottom, we see that it is the end of something. It is the end of some substance. But when we say that there is plenty of room left at the bottom, that means there is many more rooms are there, that many things are there. So we have to go in nano level to understand or to visualize those plenty of rooms. So in scale, if you see what is the scale of nano, then a tennis ball, it is around 10 crore nanometer. So it's a huge structure. For our day-to-day life, tennis ball is not very large, but tennis ball is even 10 crore nanometer. So it's a huge structure in terms of nanometer. We get some bacteria, viruses, which are very famous nowadays. They are around 100 nanometer. So a virus is around 100 nanometer. An antibody is about 10 nanometer. Suppose we are talking about glucose and water molecule. Water molecule is about 0.1 nanometer. So when we talk about nano, we are basically in this domain. Basically, we are in the domain of 1 to 100 nanometer. So in water molecule, glucose molecule, antibody, viruses, those are truly nano things. Then what is nano? If we look at this picture, if you look at this picture, this is a nasturtium leaf, and nasturtium leaf, this is what we see in our eyes, through our eyes. So nasturtium leaf has a characteristic, it is hydrophobic, so water cannot wet the leaf. So when we go in nanoscience, we see that this nano level, some nanocrystals are there. So in this nasturtium leaf, this kind of nanocrystals are there, and because of these nanocrystals, this hydrophobic nature of the nasturtium leaf has come out. So nanotechnology is during the nature. Nature has given this leaf some nanocrystals. These are the nanocrystals, and this is actually electron microscope photograph of this leaf. I will speak about electron microscope in later on. So when you see in very high resolution using electron microscope, you see this leaf, the nanocrystals. Similarly, if we what's a single human hair, so this is a single human hair, and these are the nanofibers. These are nanofibers. So nanofibers are so small compared to a single human hair. So nanoscience is very, very small. So basically in nanomaterial dimensions, we can get different type of shapes. If the all three dimensions are less than 100 nanometer, then we get nanoparticles, quantum dots, nanocells, nanorings, and microcapsules. This kind of nanoparticles or quantum dots we get. Now, if two dimensions out of the three dimensions are less than 100 nanometer, then we get nanotubes, nanoears, or nanofibers. This kind of this yellow line, this kind of nanostructure we get. Now, if one dimension is less than 100 nanometer, we get thin films or thin coatings or thin layers. This kind of yellow type coatings we get in nanofilms. So in nanotechnology, it doesn't mean that all the three dimensions should be in nano level. If the only one dimension is below 100 nanometer, then we can also consider that material is in nanoscale. So these are some kind of nanomaterials. So from these slides, we understand what is nanotechnology. So nanotechnology, it is the study of materials in very low dimensions, which is below 100 nanometer. Then why nanoscience? Why nanoscience? Because at nanoscale, the physical, chemical, and biological properties of materials get different from the properties they show in bulk state. So if I take suppose we take a carbon material, the carbon material is in a bulk state, then it shows some different properties. But when we make the carbon material in nano, then it shows some different properties. The properties gets enhanced. Suppose electrical properties get enhanced, conductivity increases, or the toughness increases. So this kind of unique phenomenon takes place at the nanoscale. Now you can ask me why this transition of properties takes place. Why the properties get changed when we go to nanoscience? The reason is that when we go at the nanoscale, then the ratio to surface to volume ratio increases. The surface area becomes very high compared to volume, which leads to altering the physical, thermal, and catalytic properties of matter. So this is where we can see that in nanoscale, when we going towards the nanoscale, the surface area increases. And because of the increased surface to volume ratio, the properties get changed. So this is how the particle size affects surface area. When you going towards the nanoscale, the surface area is increasing like this. This is an exponential increase. So the surface area increases and that changes the properties. Now the interesting thing is that many physical, many chemical properties get changed only by changing the dimension or changing the structure. So here we can see them silver and gold nanoparticles. We see here silver nanoparticles of around 40 nanometer. The color is like this. When the silver nanoparticles are of 80 nanometer, the color changes. The color is different from this. Again, 100 nanometer, the color gets changed. Similarly, gold nanoparticle, 50 nanometer, the color is like this. 100 nanometer, color is like this. So, and when we change the structure, nanoparticle or nanosphere to nanoprisms, the color again changes. So what we can say is that the color changes when we change the dimension. So here we see that the gold particle, the color of the gold particles at different sizes. This is very smaller size gold particle, the color is different. So the color changes. Similarly, size also matters. In case of technology, in artistic world, we use stained glass. Here is a picture of Angela Presertion in 1904. It was made, and it was made of stained glass. It has some colored glasses, and these colored glasses are basically the color is given through nanoparticles. So if we changes the shape of the nanoparticle, and also the color gets changed. Suppose this kind of nanoparticle, we get this color. we changes the structure, this kind of particle, then the color gets changed. Again, the shape changes, the color gets changed. Again, the shape changes, color gets changed. So this way, the shape of the nanoparticles also affects the physical properties. But in bulk level, what we see is just a piece of gold having the same color. But this piece of gold has the same color for our eyes. But when we go to nano level and we changes the structure of the nano, then the color gets changed. So this is the amazing fact of nanotechnology, that even the sizes changes, the structure changes the physical properties. It changes not only physical properties, it also changes chemical properties. I would like to give one more example, which is on sunscreen. Basically, nowadays we are using sunscreen. So how sunscreen works? So this is suppose skin, and you apply sunscreen lotion above the skin. Then three things may take place when sunlight touches the skin. Then three things may take place: absorption, reflection, and transmission. So how sunscreen acts is its absorption. Actually, sunscreen absorbs the UV and other parts of the sunlight, and because it absorbs the sunlight, it cannot reach the skin. Now, if there is no sunscreen, then obviously transmission will take place, and the ultraviolet rays and other kind of toxic rays will hit the skin, and the skin will be damaged. So how sunscreen work is it absorbs the some parts of the visible light or some parts of the solar light. So this is how absorption takes place. That is, the UV visible spectra in the solar spectra are in the range of 300 to 400 nanometer. It is in the wavelength of 300 to 400 nanometer. So if we have to block this UV part of the electromagnetic wave from sun, then we have to use some particles which are in this range. So we need some nanoparticles. That's why nowadays even some companies are using nanotechnology for cream and lotions. So why nanotechnology? Because the nanomaterials have unique properties. The nanomaterials changes properties when it goes to nano level. Some examples like catalytic property. When we go to nanotechnology, it shows better catalytic efficiency through higher surface to volume ratio. Similarly, electrical, increased electrical conductivity in many materials like ceramics and other nanocomposites. Then increased magnetic coercivity. That means the magnetic property get enhanced. Mechanical properties, we also improve the hardness and toughness of metals when we go to nano level. Similarly, optical properties, specific shift to optical absorption and fluorescence properties takes place. So optical properties get changed. Similarly, selectivity also increases. Now, why we need selectivity? Now, this selectivity is very used in medical science, because nowadays we are trying to use selected drug delivery. That means in our body, many diseases may take place. Suppose cancer takes place. Now, cancer takes place in certain area. It is not in the whole body, but in only some parts of the area. So we need to give the drug in that selected part of the area where the cancer has taken place. If we use traditional method, the medicine will go to the whole body and it will affect the other cells also, because all the cells are not affected by cancer. Only few cells has been affected. So this is a targeted drug delivery. Using nanoscience and nanotechnology, we can give the drug directly right to the cancerous cell. Similarly, in other diseases also. Similarly, in biological properties also get enhanced, and because of nanotechnology. So we can say that we get excellent properties, excellent physical and chemical properties because of nanoscience and nanotechnology. And That is why it is important. That is why we are using nanoscience. Now, because the properties of different materials get enhanced, nanotechnology is used in different parts of area, in different fields. Nanotechnology is used in transportation. Nanotechnology used environment, in energy sector, in pharmaceuticals, in agriculture, in manufacturing, in different materials, in electronics. Electronics is the most vital part, and students are very eager to know about use of nanotechnology in electronics, because we cannot live without our mobile phones, and mobile phones is a part of electronics, and nanotechnology is playing a vital role in the development of these mobile phones. So we can say that different nano devices used by different company, and because of application of nanoscience, they get different benefit. Suppose nano memory. The company use are HP, IBM. So these are laptop making or phone making companies. They use nano memory, storage memory. So the benefit is that higher density. We can we can store high memory in a very less space. Similarly, displays, Motorola, Samsung, those are using displays. So in case of nanotechnology, we get brighter, lower power, and inexpensive displays. Then transistor, IBM and Intel are doing, using transistor, and nanotechnology enable them low power processing and memory. Similarly, data storage. The company using is IBM is very famous in producing data storage devices, and we get very high density data storage devices because of nanotechnology. 1 TB per square is very high. Otherwise, in earlier times, computers were very big. We need 2-3 rooms to place one computer to storage 1 TB data. But nowadays, we can take a hard disk in our pocket, which can storage up to 1 TB data. And these things has taken place because of nanotechnology. And future is that nanocomputer. HP, IBM, Hitachi are trying to produce nanocomputer. And in case of nanocomputer also, we'll get size, performance, and mobility benefits. All these benefits, all this technological development are taking place because of nanotechnology. So I would like to talk about mobile phones. So in case of a mobile phone, there are different electronics. We have optics, we have acoustics, we have displays, coatings, antennas, paints, batteries, everything. And everything is using nanotechnology. And the application of nanotechnology is helping or enhancing the properties. How it enhancing? Suppose the coating. So nanocomposites are stronger, tougher, and lighter materials. So the coating is making very good. Similarly, I have already talked about nano displays. Nano displays very high, very large, very bright, lower cost. Similarly, nano antennas, because of using nano antennas, the antennas has become very small. Earlier days, this kind of antenna were there, but nowadays this is not there in our mobile phones. The antenna cannot be seen. It is inside the phone. Similarly, nano power. It is very developing technology. Nano power, the battery. We need more battery backup. We are getting 4-hour, 3-hour, 7-hour battery backup. We are trying to develop more battery backup. And myself, I am working on rechargeable batteries also. I have done my PhD also in rechargeable batteries. So we are trying to develop high density batteries so that we can get very small batteries and it gives power for longer period of time. And also compatibility should be very large. So we are trying to develop these properties, and these properties can be developed using nanoscience. So in these things, we are using nanocomposites. What is a nanocomposite? We can get different materials which are in nano domain. Those are nanocomposites. And even we can mix 2-3 materials and we can make a composite like diamond, buckyball. Buckyball is a carbon material in a particular football type structure. It is a carbon 60. We call it C60 material. So it is in the structure of a soccer ball. That's why it is called buckyball. So buckyball also is in the nano domain, and because of this, it's in nanoscience. In nanosize, it gives enhanced properties. Similarly, graphene also. The development of graphene is tremendously changing the technology. We are developing very much in different electronics, in mobile phones, in laptops, because of the production of graphene. Graphene is nothing but it is a layer of carbons. So if we get many layers of carbon, then we call it graphite. Graphite we use in our pencils also, we have graphite. So those are graphite. But if we get one layer of carbon out of that graphite, we get graphene. And because we have not sensed anything from the graphite, from the pencil we just have sensed the dimension. We have taken one layer of graphite, that is one layer of carbon, and then the properties get changed. The electrical property of graphite tremendously changed when we take one layer of carbon or one layer of graphite, which is graphene. So the nanotechnology is changing the properties. And what more thing is that in case of nanocomposites, we can use nanomaterials which can be specific application, and the properties can be tailored. That means we can tailor the properties using the variations of product producing them, variation of the size and shape of the material. So according to our application specific, we can tailor the properties. That is a very positive thing of nanocomposites. Another good thing about nanotechnology nowadays is going on is nano emissive display. So earlier days, this kind of TV screen were used, CRT, cathode ray tube. It's a very large structure. So TVs in earlier days were very large. The backside becomes very bulky. And those TVs or CRTs used, actually electrons comes from 3 cathodes. Okay, so there are 3 cathodes over there. So electrons from these 3 cathodes scan the screen and they produces the display, or they produce the image. So electrons comes from only 3 cathodes. So very less number of electrons has come. Less number of electrons means less is the resolution on the display. So the display we cannot expect very high resolution screen. But because of the development of nanoscience and nanotechnology, now we have produced nano emissive display. What we do here is that we take carbon nanotubes. We can develop carbon nanotubes like this on some wafers. We can take a sheet of something, some wafer. Generally, it's a silicon like that. Then we can deposit the carbon nanotubes there, and we can produce cathodes. And since the carbon nanotubes are in nano dimension, we can produce millions of cathodes. So basically, we get millions of cathodes, which enable a thin, high clarity flat screen TV. So just a flat screen. From here, we deposit the carbon nanotubes, and from these millions of carbon nanotubes, electrons comes out. We get millions of electrons to produce the image. So we get very high resolution because of carbon nanotubes. So this is a very good development in electronics nowadays. And what is the future? So with step by step, because of nanotechnology, because of the advancement of the properties of nanotechnology, we are getting more in future. So I think you have seen another movie. This kind of scene you have seen It's a scene from Terminator 2, Judgment Day. So this is a T-1000 robot. So it can sense the structure. This is a robot which can sense the structure, that anything it touches. Suppose it touches this man, then it can take the shape of this man. This robot takes this, touches the floor, it can take the shape of the floor, and it can sense its structure. Also, it can turn its fingers into weapons. So this kind of this is the T3 robot shown in Terminator Judgment Day. So what are the properties of the material of this robot? In the movie, it is explained that they have used nanotechnology to produce this robot. So what is the material is called? In the movie, it is called mimetic polyalloy. The T-1000 Terminator robot is composed of mimetic polyalloy, a liquid metal that utilizes nanites for shape-shifting abilities. So this robot has the ability to mimic anyone. It is in physical contact. So it is the future of nanotechnology. Although it's a very old movie, around 1991 or 93 movie, but it's at the time it is a fiction. But sometimes fiction becomes reality. In many times we have seen that the earlier fiction has become nowadays reality. So in future we may able to produce this kind of robot or this kind of material. And what is the basic for developing this kind of material is nanotechnology. One more future thing is nanorobotics. I already have said about like the targeted drug delivery. So we are also using nanorobots. So this kind of nanorobots can be injected into our blood. And this kind of nanorobots can fight with the viruses or bacteria which comes into our blood. So these nanorobots increases our immune power. Okay. So apart from increasing immune power, they also there may be also targeted drug delivery, which I already discussed. So this kind of future of nanotechnology can take place. Okay. And for that, we have to do much more research. So with this, we have come to know what is nanotechnology and why nanotechnology. What is nanotechnology we understood, why nanotechnology we understood, and now how. So how to produce nanomaterials and how to characterize the nanomaterials, how we produce nanomaterials, and how we know that the nanomaterials has been produced. So basically, there are two ways to produce nanomaterials. These two methods are top-down method and bottom-up method. And there are different characterization techniques like X-ray diffraction, transmission electron microscopy, scanning electron microscopy, Fourier transform, infrared radiation spectroscopy. So this kind of technology is there to characterize the nanomaterials and to know that the nanomaterial has been produced. So first of all, let's discuss what is top-down and bottom-up method. So as the name suggested, in case of top-down approach, we take a bulk material and we cut it down until we get nanoparticles. But obviously, we need some machines, we need some sophisticated machines to cut it down. Okay. So top-down approach refers to actually slicing or successive cutting of bulk material. We get nano-sized particles. So this is a top-down method. The other one is bottom-up approach. It is the opposite. We take smaller atoms or smaller molecules. We make clusters of atoms or cluster of molecules, and then we get the nanoparticles. Okay. So bottom-up approach refers to the build-up of material from bottom, atom by atom, layer by layer, molecule by molecule. So depositing atom by atom, we can get nanomaterials. So basically we have two approaches to produce nanomaterials. To cut a bulk material into thin pieces in order to get nanoparticles, that is the top-down approach, or layer by layer, we deposit the atoms and we get the bottom-up approach. So it's in grinding, ball milling. So ball milling is a very effective method. So in case of ball milling, we use very high energetic ball milling. In that we can of reacting species. So we take some reacting species, we send some catalytic particles, then some reaction takes place, and layer by layer the deposition of nanomaterial takes place. So these are the two approaches by which we can produce nanomaterials. So now we will go to how to characterize the nanomaterials. So in case of characterization, first one is X-ray diffraction. So before going to X-ray diffraction, I would like to talk about on what principle the X-ray diffraction works, or this XRD machine works. And probably you know about Brake's law. Any undergraduate student of physics, actually there is, I think in Guwahati University, they have the syllabus in 6th semester, Brake's law. So what happens in Brake's law? So actually, Brake, the father and son, William Henry and William Lawrence Brake, they have assumed that the atoms in a solid are arranged in a particular arrangement. So when we take a solid, when you take a periodic structure, when you take a crystalline structure, the atoms are arranged in some definite manner. So we get layers of atoms in definite shape and sizes. So these layers can be taken as planes. This is one plane of atoms. This is another plane of atoms. So this kind of planes we can take. So when we introduce these materials with X-ray, then interference can take place. And depending on whether constructive interference takes place or destructive interference takes place, we get bright spot or dark spot. And this is the Brake's law. I mean, this is the condition for constructive interference. 2d sine theta equal to n lambda. D is the interplanar distance. So D is the distance between two planes. So if this 2d sine theta equal to, this is the integral multiple of the wavelength of the X-ray used, this condition takes place, then we get bright spot. Their constructive interference takes place. So from this law, if we strike any material with X-ray, then we can get some constructive interference at some particular places. By using those particular structure, we can say that whether our material has been formed or not. We can even find out the particle size from the structure. So when we talk about planes, I already have said that the atoms are arranged in some planes. And these planes are characterized by HKL values, Miller indices. You know about Miller indices. So HKL values gives us the plane. So this kind of planes we get, this red one. So here the Miller indices is given. So we get different kind of planes. The planes may be like this, like this, like this, or this is like this, or so we can get different kinds of planes. When the interference takes place in different kinds of planes, we get constructive interference, and then we get a peak in the X-ray pattern. So this is the X-ray pattern. We are changing the angle. We are getting different peaks. So like this. So from this plane, we are getting this peak. We are changing the angle from this another plane. We are getting another peak. From another plane, we are getting another peak. So from this XRD pattern also, we can we can characterize the nanomaterial. But you can ask me, if constructive interference takes place, constructive and destructive interference takes place, then how these peaks we get? We should, from Young's double slit experiment, we know that there are some spots actually we get. So why those kind of spots we are not observing in X-ray? But the answer is yes. We actually observe scattering pattern, something like this. Okay. So this is the actual XRD pattern, what we observe in the computer screen when we carry out the experiment. But if you study some papers and some research works, you will not able to see this kind of images, but rather you will see this kind of images or this kind of patterns, because actually this kind of pattern makes clearly tells us what kind of material is that. Okay. And from this to this, how it takes place? It takes place from Fourier transformation. Undergraduate physics students from first or second semester, they study Fourier transformation. So Fourier transformation can be used to transform some signal. Suppose we are streaming our live session to YouTube or to our some TV channel, then Fourier transformation takes place. Our image is using Fourier transformation, our image is transformed into signal, and again in the TV or in the YouTube channel, the anti-Fourier transformation takes place and the signal is again processed to image. So I'll not go in detail how it is done. It is done by using some computers. So from this image, we get this kind of structure. Okay. And one more thing is that different materials have different planes. I mean, if I take gold material, we have some definite planes. If I take silver material, then the silver has different planes. That means this constructive interference takes place at a particular angle for one particular material. So where it has taken place, where this peak has come, from that also we can characterize the material. We can say that if this 100 constructive interference pattern has come at 30 degrees, then it is of course this material. In case of Y material, that will be changed. So this is how using XRD we can analyze. So here I have shown you how the interference takes place. With the monochromatic X-ray takes place on this random crystal structure. The detector is changing. The detector moves like this, and at some particular values we get this kind of. This is going and going, and again here constructive interference takes place. Again here constructive interference takes place. So this is how XRD works. Okay, so this is a true picture of XRD machine. We have some source. We place the source here, from X-ray comes here, and the detector is here. So the detector moves, the 2 theta angle changes, and we can get the X-ray images. So this is one actual X-ray. I think you can recognize this person. So it's me working with XRD machine. So this machine is somewhat modified. You can see some structures are there, but basically if you go in some institutions and see the XRD machine, it's not like that. It's basically like this. Here it is because we have some arrangement. We have some different arrangement for a particular experiment. So we have some different accessories here. And this is a particular X-ray structure of barium titanate. So this kind of X-ray structure we get. So the next characterization technique in case of nanotechnology, very important characterization technique is transmission electron microscope. So this is a typical view of a transmission electron microscope. So this is the microscope. Now using this transmission electron microscope, which we frequently say is TEM. So using TEM, we can directly observe whether the nanoparticle or anything nano or nanofiber or the nanomaterial has been produced or not. It's directly give you the image of the nano substance. Now, what is the physics behind it? See, we have discussed earlier the XRD machine. We have discussed the physics behind XRD. The physics behind XRD is Brake's law. So this is the paraphernalia of physics. Brake's law is the paraphernalia of physics which is used in nanotechnology, which is used to produce the XRD machine. So what is the physics in transmission electron microscope is quantum tunneling. So where you first heard about quantum tunneling, in case of me, I heard quantum tunneling in Lewis Carroll novel. It's a very famous novel, Alice in Wonderland. It's a novel for kids. Actually, what in a particular chapter of Alice in Wonderland, Alice and another bee, they got trapped inside a room. There is nothing inside the room, no window, no door, nothing. They cannot escape from the room. Then what the bee does? Then the bee suddenly start moving very fast. When the bee start moving very fast, at a certain point of time, it goes out of the room. Then Alice understood the procedure. So she started also moving with very high velocity. And at some point of time, she also goes out of the room. So this is actually quantum tunneling. In case while we are studying the novel in class 3 or 4, Alice in Wonderland, we never understood that it was quantum tunneling. We thought that some magic has taken place, and that's why Alice has gone out of the room. Now, Lewis Carroll was a professor of mathematics. So he knew quantum tunneling, and he has applied those physics in his novel. So what quantum tunneling is? The very basic idea is that at quantum level, we cannot say something as particle or wave. It shows dual nature. Electron shows dual nature. Electron behaves as a wave. So in classical picture, electron is a particle. So when it comes into a barrier, suppose a wall or some high potential energy barrier, so the particle cannot pass through the barrier. Okay, it will be reflected back from the barrier. This is the classical mechanics view. It cannot pass through. Whatever be the energy is given, it requires some amount of energy higher than this particular value, this particular wall. And in case of a human being, it is never be possible to surpass or to go through the wall. But in quantum mechanics, what happens is that we consider electron as a wave. In quantum mechanics, we take any particle as a wave. So when the wave incident on some barrier, there is always some probability that it passes through the barrier. So this is quantum tunneling. So this is how quantum tunneling takes place. This is a wave. The wave is coming, and this is suppose the barrier. Now there is some probability that the wave passes through it. Obviously, some part will get reflected. That is the reflectance, and this is the transmittance. So when the wave incident on the barrier, there is always some probability. It may be very minimum, but there is always some probability. But the case is that for that, we need very small particle which can show the wave nature. Obviously, in real world, a human being like Alice cannot pass through a wall because we cannot observe quantum world in case of Alice because she is a very large structure. We are very large for showing the wave nature. But in physics, it is correct. If somehow our velocity becomes very high or we become very small like electron and we are able to show the wave nature, there is always a probability that we can pass through the barrier. So in case of transmission electron microscope, this particular physics takes place. We place the sample at some point, then we place the sample at some point, we incident some very high energetic electrons on the sample. Then what happens is that because of the wave nature of the electron, it passes to the sample. Now, the thing is that when it passes to the sample, it interact with the electrons of the samples. So ultimately, it gives the picture of the sample. And that tunnel through electron is used to produce the image. That is why it is called transmission electron microscope. The electron has transmitted. So this is the basic of transmission electron microscope. We have some electron source here. From this source, very high energetic electrons are produced. Then we have some magnetic lenses. These magnetic lenses are used to focus the electrons. That means we can focus the electron in some specific part of our sample. So suppose the sample is here. This is a sample holder. So the sample is placed here. Then the electron comes, then the electron passes through because of quantum tunneling, and it comes to here. Then we produced the image. So obviously, we need some arrangement for TEM specimen. We need some carbon grids where the sample is placed. The grids look like this. So here the sample is placed, and then this is the sample holder. The grid is placed here, and then it is placed inside the TEM. Okay, so this kind of some mechanical arrangement we need. Then the electron passes to the sample. And these are some results of TEM images. Okay. So this is the TEM image of gold nanoparticles. Now, in case of any electron microscope image, you'll always see some scale. Here it is slightly not visible clearly, but from here to here, this is 200 nanometer. In this picture, it is somewhat clear. From here to here, it is 200 nanometer. This means this much distance is 200 nanometer. Then you can make out what is the size of the particle. Obviously, it is a nanoscience, nano dimension. If it is 200 nanometer, it is around 10, 20 around nanometer. So this is how, using transmission electron microscope, we can directly observe the formation of nanoparticles. Similarly, this is the TEM image of graphene. I already talked that graphene is a single sheet of carbon. Okay. So it's a single sheet of carbon. And we can produce the TEM image from here. That we can see the thickness. We can see that these are layers. So from TEM images, we can see the graphene. So we can see different structures also. Like nowadays, people are producing different structures. These are flower-like structures. Some producing cactus-like structure. So different structures people are producing, because these structures also changes the properties of the material. And we see that these are flower-like structure of some material, some gold material. Okay. So in nowadays, at present, this is the TEM image of some virus. I think you can recognize this virus. Of course, it is the TEM image of coronavirus. So what we generally see in ad and some things, the coronavirus, actually that is the artistic view of the coronavirus. But what is the actual image of coronavirus? This is the actual coronavirus. It is taken from transmission electron microscope. So here some proteins are there. Actually this is an RNA structure. Coronavirus is some RNA structure. It is some protein falling here. So because of this hair-like structures taken place. Because of this, our artistic view, the green color artistic view comes from this. Okay. So similarly, we can observe also HIV virus under electron microscope. So these are fully mature form of HIV virus. You may be interested to know about the size. So coronavirus is about 250 to 300 nanometer in size. So from here to here, it is around 250 to 300 nanometer. But HIV virus is much smaller. It is around 50 to 60 nanometer. So HIV virus is around 60 nanometer in dimension. Now, how we produce medicine? in case of viruses. What we do is that if we give the medicine or a vaccine, what it does, the medicine actually, suppose this is the HIV structure, the medicine actually, it will trap the HIV virus. Okay, the medicine will trap the HIV virus and the virus cannot move, and then it will die out. Okay, in case of coronavirus also, the medicine will try to trap it. But till now you can ask me why there is no medicine in case of HIV virus. Because the particular or a peculiar behavior of HIV virus is that it can changes the structure. Here we are seeing a spherical kind of structure. But if we try to entrap the HIV virus with medicine, obviously the medicine will be in some protein form because its virus is a protein form. So when it will try to entrap the virus in the structure, the HIV virus changes the structure. It will changes from this spherical structure to another structure. Now the medicine fails. It cannot bind the structure. So there is no medicine till now for HIV. In case of coronavirus also, research is going on. I hope in case of this corona, it will be possible to make medicines and vaccines. But I don't know about HIV because HIV is very peculiar virus. We can hope that in future science and tech is, or nanoscience, see how nanoscience is applicable. Because of transmission electron microscope, which is the product of nanotechnology, we can see these viruses directly. Okay, so when we see the viruses directly, our research got a very tremendous plus point. So after transmission electron microscope, another very vital instrument is scanning electron microscope. It is very similar to TEM or TEM. Okay, here also we use high energetic electrons, highly energetic electrons. So this is a chamber where the electrons comes, and here the sample is kept. So this is the working model. We have some electron gun, then the electron passes through it. But the basic difference between TEM and SEM is that in case of scanning electron microscope, we use the scattered electron. In case of transmission electron microscope, we use the transmitted electron. So suppose this is a sample. This is the sample of the material. In case of TEM, the electron passes to the sample, and the passed through electron we are using to produce the image. In case of scanning electron microscope, the electron hit the sample and some electrons scatter back, and that scattered electron is used. So obviously, in case of SEM, we need less energetic electron. Okay. So we need less energetic electrons. But in SEM or scanning electron microscope, we get very high resolution of images. So these are some same images of pollen grains. Obviously, pollen grains are there in flowers. Okay, inside flowers we get some pollen grains. So this is the actual structure of pollen grain inside the scanning electron microscope. We can very nicely view what the pollen grains looks like. Similarly, these are the some images of different nanostructures. These are nanosphere kind of thing. Now this is 2 micrometer. Obviously, this is in not nano, but it is in micrometer. Okay, basically nanoparticles are observed under transmission electron microscope, and the micro level particles are observed under scanning electron microscope. Okay, and of course this is the front head image of a mosquito. So this is the head of a mosquito under SEM. So you can nicely see very fine structure of a mosquito. Now with our eyes, we cannot even see the mosquito clearly, but with the use of scanning electron microscope, we can clearly visible what is the internal, what the physical structure of the mosquito head. So it's a tremendous technology. of nanoscience. So after saying many things, I think we have talked about what is nanoscience, what is nanotechnology. We have talked about why nanotechnology is used, and we have talked about how we characterize and how we produce nanomaterials. So after all these things, you may be interested to know what personally we are doing, what I have done in our work. So actually, I would like to show my very few works of mine. That is, I work on polymer electrolyte nanocomposites. So what is a polymer electrolyte? So basically, in case of a battery, we get three different parts: two cathodes and one electrolyte. Two electrodes and one electrolyte. One is anode, one is cathode, and the electrolyte. So in case of very large batteries, we use some liquid electrolyte, like in our inverter battery or in our car battery, we use acid as the electrolyte. Okay, but if we use liquid electrolyte, there are some drawbacks with liquid electrolytes. The first one is the size. We get very high, very large size batteries, okay, which is not possible to carry. I cannot carry a huge battery with my laptop to give the power. I need very small batteries. The battery may be small, but we need very high power. Okay, so this is one particular drawback of those liquid electrolytes. Okay, so in case of polymer electrolytes, we get thin, paper-like structures. Now, when it comes in the thin paper-like structure, now we can get flexible design flexibility. Okay, so these are the advantage of polymer electrolyte. Why we use polymer electrolyte? It gives design flexibility. First of all, that is the primary thing. Okay, then we get high energy density. We get thin film. We get no leakage of liquid electrolyte. In case of liquid electrolyte, there may be some leakage. We get also low cost. Okay, but of course, everything is not the correct one. We get also drawbacks in case of polymer electrolyte. The main drawback of polymer electrolyte is the low conductivity. Okay, say one basic difference in conductivity of cathode and electrolyte is that in case of cathode or in case of the electrodes, we need conductivity of electrons, like the current. Okay, the current actually conductivity of electrons. The electrons flow, but in case of electrolyte, the ions actually flow, not the electrons. It may be lithium ion. You can see your mobile batteries, they give a lithium ion battery. So that means the polymer electrolyte is of lithium ion, so positive ion. So movement of positive ions take place. So if we want to get very high conductivity material as electrolyte, we need very high conductivity. But in case of polymers, one drawback is conductivity becomes very low. One more thing, we get low interfacial stability. What it means? That means when we produce a battery, it is the electrode and it is the electrolyte. So they come in physical contact. When they come in physical contact, some passivation reaction takes place. And because of this passivation reaction, the stability decreases. Okay, because of that, with time, the battery becomes not powerful enough. Okay, so the life of the battery decreases because of those reactions, because that is the interfacial stability. So in case of polymer electrolyte, interfacial stability is very low. So these are the drawbacks with polymer electrolyte. Now we have to improve this. Okay, how we can improve this? The primary method is dispersion of filler particles. That means with the electrolyte, we disperse some particles, and those particles are in. So by giving some nanoparticles or by giving some nanomaterials, we can increase the conductivity, we can increase the interfacial stability. Okay. So these are the applications of the polymer electrolytes. In lithium ion batteries, polymer electrolyte used in vehicles, in electrochemical devices, in laptops, batteries of laptops, then in electrochemical windows. What is electrochemical windows is the thing here it is going on. I mean, with time it blocks the sun rays. It can dark itself or it can become fainter depending on the voltages we apply. Okay, in some aircraft it is used. When the sun rays comes in contact, very high sun rays, then it blocks the sun rays. It becomes darker for the comfort of the passenger. So this kind of electrochemical windows, we use polymer electrolyte. And in our day-to-day life, it is going on, the list is going on. So how we produce this polymer electrolyte? So I would like to show what myself has synthesized. Okay, so this kind of electrolyte, this is a thin kind of paper-like sheet. Okay, this is one kind of polymer electrolyte. We have used some nanomaterials, which is called nanorod. Okay, we have used nanorod here and nanosilic. In this case, white one, we have used nanosilicates, some layers in nano level. Okay, the layers are in nano level, layered structure we have used inside the polymer electrolyte to enhance the properties. Okay, so this is what happening. We have in a battery, we have anode, we have cathode, then we have this electrolyte. Okay, so this electrolyte we can solvent molecule and we can increase this electrolyte. This is the polymer electrolyte. Okay, directly I have synthesized this one. In another one here, some layered structure is used as nanofillers, which is called layered silicates. Here some nanorod is used, polyaniline nanorod is used. Okay, so basically when we use the nanorods, when we use the layered silicate, this has tremendously enhanced the properties. Now, these paper-like thin structures can be used in this kind of battery. When you see the mobile battery, the laptop battery, here some electrolytes is already there. And those are in paper-like structure. Okay. So this is how the miniaturization of is taking place. We are developing, we are getting safe versatility because of the nanotechnology. Okay, so in the next slide, I would like to show another technique we have used for the formation of nanocomposites. Okay, and this one is swift heavy ion irradiation. Okay, this is a new technique. In this technique, we used some high energetic ions. Okay, we take a material, we take a composite, and suppose this is the material. We allow the high energetic ions to pass through it. When it passes through it, it creates some nano level changes. Because of the nano level changes, the properties of the material get enhanced. I hope you can recognize this fellow. It's myself doing some experiment. Actually, this is the one. This is a vacuum chamber. Okay, this is the kind of structure where the material is given. Then this material is put inside this vacuum chamber, and the ions comes through this kind of pipes and this kind of pipes. Okay, so this is the pipe through which the ions come, and at the end of this pipe, this vacuum chamber is there. So, and from where the ions come? From this part. This is the institute, Inter-University Accelerator Center, New Delhi. So basically I worked there while doing my PhD. So the ions comes from here. It comes through this. It goes in many times. It increases the energy of the ions. You know about CERN in the Geneva, in Switzerland. They're striking some protons collision, and they are getting new materials. or subatomic particles, new subatomic particles they're getting. So here in this part, the energy of the ions is increased. Then inside this is actually inside the underground. This room is underground. So inside this through these pipes, the ions comes, and here it is strike. These are some other experiments related with this. Okay. So earlier slide I have shown you, this is the polymer electrolyte synthesized. Okay. When I have given inside this chamber, okay, so this is how irradiation takes place. You can see the black spot. You can see the black spot here. Obviously, I have cut the sample into smaller pieces, and some area is taken, 1 centimeter by 1 centimeter area, generally it is taken, where the ions is strike. Because of the ions, the color of the this has changed too. Because of the striking of the ions, color has taken changes. Not only the color, actually it has changes the entire physical and chemical properties of the electrolyte. So this is a schematic diagram, how the properties get changed. Actually, ions changes the structure of the polymer inside this material, and because of this at nano level, the properties get changed. Okay, and these are some direct results of our work. So this is the TEM. We have already talked about transmission electron microscope. So this is the image of some layered structure. So you can see that directly nano level layer. So from here to here, this is 20 nanometer. So these layers are very, we have synthesized, we are able to synthesize very, very low nano level layers. So these layers synthesize the entire properties. This is the direct X-ray observation. Okay. This is the scanning electron microscope, same. Actually, same observed somewhat outside. So this is the same image. You can see the porous kind of structure. Inside this, if you go deeper level, very high deeper level, you will see this kind of thing. So same is somewhat upper level observation. Same is in deeper level observation. Okay. One more nice thing you can do with SEM is that actually you can do elemental analysis. Elemental analysis means what are the elements produced in a certain area. You can find out using scanning electron microscope. So this is the elemental mapping. This is called mapping, electron mapping. Okay. Suppose I take this area. Okay. I can this area and I can scan this area with electrons to see what are the materials produced. So, and we keep some color for each kind of element. Like here we give red kind of color for carbon. So we can see that carbon is there. We give green for fluorine, aluminum, bromide, magnesium, silicon. So these are the materials that are produced. Actually, we have used some ionic liquids and some polymers. Actually, this carbon, fluorine, magnesium, bromide, these are from these materials. So we expected that in this area, these elements will be present. Okay. Actually, when we do research, then we have to publish the work in some papers. So after doing this kind of works, we have sent it to a journal, a very high reputed journal, Journal of Membrane Science, with an impact factor of around 7. 7 is very moderate, very decent impact factor. Impact factor actually gives the idea of the reputation of the journal. So when we send the work to a journal, they have asked that proof that the materials you have telling it is actually present. And because of the question the reviewer has asked us, we again carried out the experiment, and by using scanning electron microscope, we have proved that carbon, fluorine, aluminum, magnesium, silicon, these are the materials actually present in that. Okay. So after this clarification, the work has been published in the journal. I would also like to show one more very interesting property of nanoscience is this. This is the result. This is the result of contact angle measurements. So what contact angle measurements give us? It gives us hydrophilicity or hydrophobicity. So if it is less than 90 degree, the contact angle is less than 90 degree, it is hydrophilic. That is, the water can wet the substance. If it is more than 90 degree, the water cannot wet the substance. Okay. So what we have observed is that when the nano size changes, the material actually changes from hydrophilic to hydrophobic. It is a very interesting idea. When the nano size is very less, we get 78 degree of contact angle, which is showing the hydrophilic nature of the material. But when the nano size, we are decreasing the nano size, we are getting 130 degree. Okay. So hydrophobic, better hydrophobic materials are very good because it cannot wet the material. If your laptop screen or laptop material is hydrophobic, if you pour some water, it cannot wet the material. It is very good. Okay. So by using nanotechnology, we are able to produce hydrophobic material. So that is also, and I would like to show you some papers where we have published our works. So Electrochemical Acta we have published, Solid Dynamics, then Journal of Membrane Science, Materials Letters. So these are some very good journals where we have worked. So with this, I would like to conclude today's talk. So in conclusion, we have talked about paraphernalia of physics in nanotechnology. And what we have talked is that we have learned about what is nanotechnology, then why nanotechnology, and then how nanotechnology is achieved. In any scientific temperament or any scientific thinking, these three questions are very important. You always remember what, why, and how. If you can answer these three questions, you can understand the basic points of this subject. Okay, so I tried to answer what is nanotechnology, why nanotechnology, and how nanotechnology is achieved. And while doing so, we have talked about XRD, we have talked about TEM, we have talked about SEM. So these are the conclusions. But before concluding my lecture, I would like to give one example. So this example will give you how we should think. So in science, how we should think. Okay, that is very important because in science, remembering something is not, somebody says that, oh, I can remember what is written in 70 pages of Griffith's Electrodynamics. That is not important because I can take my mobile and I can directly go to the 70 pages of Electrodynamics by Griffith. That is not talent. The talent is how you analyze what is written and what new thinking you have put forward from the written sentence. Okay, so for this example, I would like to give one poster of a very great movie, The Silence of the Lambs. Obviously, if you see the list of 100 greatest movies, it is one of the 100 greatest movies ever made, The Silence of the Lambs. So if any viewer observe the poster, it is just a poster of a movie. But if you analyze and if you go deep, you'll see that the entire movie is analyzed in this poster. How it is analyzed? It is analyzed like this. The red eyes, the red eyes gives the feeding of people using others for own gains. This is kind of the very nature of what is inside the story of the movie. The left side is white, the right side is dark. The left side, white skin, it determines death and beauty and innocence. Okay, sorry, it is the beauty of innocence. Here in the right side, it is dark. It gives danger. It is shadows. It is death. So it also says that the past is beauty. The future is very dangerous. Future is death. Okay. Then this is a moth. Moth is a sensing structure. Like a moth to the flame, attracts to danger. So the movie is telling that the story is going to be dangerous from past beauty to future dangerous. Then this is a skull. So skull gives death. So the one inherent the inherent story of the movie is related with some kind of death. So it is like that. Okay. So this whole poster actually gives you the whole story of the movie. It's simply a poster. Now, even going deeper, you can see this. Even this head of the moat is like this. And inside this is this. So this is a famous portrait by a painter. So this kind of, actually this portrait resembles the meaning of that, like that. So it's a kind of thing. So just from a film poster, for some people, if you go deep, you analyze the whole movie, you go deep, you see the artistic point. Again deep, you can deeply analyze what is the artistic beauty of the work. Okay. So in every work, we have some artistic beauty. And I am telling you, always analyze and believe in your eyes. In science, we need analysis. Thank you. Thank you very much. I am handing to Anouk.
Okay. Hello. Oh, it's okay.
Yeah.
Hello. Thank you, sir. It was a
Yes,
lovely
yes, yes.
experience, sir. Thank you, sir, for your lecture. Sir, I have
Yes,
lots
yes.
of queries and lots of questions from the students.
Yeah, yeah.
So let me take some questions. Okay,
Mhm.
sir. It's a question from Amit Tiwari. He says, sir, air and water are polluted day by day.
Yeah.
Sir, in nanotechnology, what are the challenges and
Mhm.
emerging benefits for water and air treatment?
Yeah, we can use nanotechnology in some making some pollution-free environment, or we can harvesting also in different kind of fields. We can use in cars also, in carbonator also. We can use some nano devices which will filter the air. Okay, in some industries also. Basically, it is used in many industries because leaving the material or depositing the material somewhere, those are passed through some filters, and those filters uses nanotechnology. So because of this, our environment are getting benefits. Okay.
Okay, sir. It's a next question from Neil Pawan Sharma. He
Yeah.
asks, sir, nanomaterials exhibit change in color with
Yeah.
respect to change in shape. So,
Yeah.
is there a possibility of the some shape which can be allow light to pass through it or behave as a transparent material?
Yeah. Actually, if you want to pass through the light, actually, how we can pass through the light? That means we have to changes the permittivity of the material. Okay. So actually, we can call it as a metamaterial. So we cannot produce metamaterial by using nanotechnology at current technology, but maybe in future we can able to produce metaparticle. In that case, we'll be able to get negative permittivity material. So in that case only the light wave can pass through it. So suppose this is a metamaterial. So if the electromagnetic wave is incident on it, it has to go past through it. Okay. So in that case, sometimes we may be able to use. In that case, we can use invisibility concept also. And in some aircraft, it is already using the stealth technology. Like the US is using the B-4 bomber, where stealth technology is used, where the shape of the aeroplane or the shape of the fighter plane is very reduced. So when the country where it's entering, the radar when give the signal, it shows it's like a bird. Okay, it doesn't show the very high, very large structure of the plane, but it shows this very tiny structure. So people think that a bird is coming, not an aeroplane is coming. Okay, so this is still technology. So this kind of technology we are developing, and we hope that in future we may be able to produce. Okay.
Okay, sir. I'm taking another question.
Yeah.
It's from Anomalous attendee. He
Okay.
asks, sir, what is the basic theory behind the teleportation? Teleportation.
Oh, teleportation is actually it is a quantum kind of thing. That means you have to place some machine at some place and another machine in some another place. Then you can, in one machine, you have to convert the material into wave. Okay. Then the wave will go through, and in the other machine where it is placed, it will collect the wave, and it will again give that material. So since electromagnetic wave travels very fast at the speed of light, so actually we will be able to teleport the whole material. Suppose I'm going inside the machine, the machine convert me to wave. The wave will go very fast to the other place. Suppose the other one is placed in New York, then within seconds I will be able to go New York. This is the very basic theory. But the thing is that at the current technology, we cannot make ourselves as a wave. It's a very challenging technology.
Yes,
Okay.
sir. Okay, sir. I'm taking a question from YouTube streaming. And
Yeah.
this was a question put by
Yeah.
Jem Taka. He asks, sir, what is the feasibility of using TEM in biological sample?
Yeah, we can use TEM in many biological samples. But we have to remember that actually I have not worked on biological samples. But what is that the electron, when it passes through, it can destroy the sample. Okay, and moreover, in some materials we have to do some coatings also. Suppose we are using gold coating, so that the electron, actually it is very difficult to stabilize the electron wave, because it is very high energetic electron. It is destabilized. We cannot stabilize the electron at that particular place. So for that we use coating. When we use coating in some biological material, it also may destroy the material. So one more other thing is that vacuum. So in TEM we need very high vacuum. So we have to study, if you are using some biological material, then you have to study what are the precautions you have to take. Does very high vacuum will destroy it? Does very high energetic electrons will destroy it, like that? So if it can destroy the protein structure, so you will not be able to get the actual thing you want. So first you study what are the things. You can also mail me, I'll try to find out.
Yes.
Yeah.
So, dear participant, will give the email ID of Dr. Anup sir, and definitely he will answer all your queries. So, yeah, thank you, sir. Once again, it was lovely
How
to hear
was
you.
the
Hear
talk?
from you.
Yeah.
Yeah, also
Is
excellent,
it
sir. I
okay?
have excellent. Yeah, it was excellent.
Yeah.
I was behind the screen for. I have not get up from the screen. It's my seat, sir. So it was very good,
Okay.
sir.
So
Thank
Anup,
you.
yeah,
Thank you so much, sir.
thank you very much.
Okay, sir. Thank you, sir. Looking forward to meet you in a future also, in a future webinars also, sir.
Yeah, sure. Thank you.
Thank you, sir. Thank you, sir. And for information for the participant, that tomorrow our program will be starting, day 2 will be start from 10 a.m. We have given the schedule to you all, and the new webinar link and WhatsApp link will be provided in your registered email and in the official WhatsApp group also. And the feedback form will be issued also in tomorrow also. So please join the webinar before 10 a.m. So thank you. This is what for the first day, and it was a successful day. We don't have any technical glitches from the speaker side and from the host side also. So it was a very successful one. So thank you all.